right. Thank you all for joining this technology summit. So this is day one. We're going to cover anaerobic digestion and related type processes, as well as in this afternoon, looking at some dryer technology. Thursday, it's going to be more like the thermal processes and advanced technologies that we'll look at. So please feel free to join us on Thursday as well. For those in the room, there's a sign-in sheet. Hopefully you parked across the street and not here in this parking lot. If you did, please go move. Now's the time. See, exits this way. There's also a water fountain and bathrooms right outside the door. And so in front of you, there's these microphones. They're all turned on. Right now, mine's the only one that's green. You just press a little button. So that way people can hear you virtually. So when you ask questions or have conversations, please make sure to turn on your mic so that everyone can hear and we don't have to repeat questions. So for those virtually, we will have the presenter share their screen. Hopefully we're going to do 20-minute presentations. So that is up to presenter of how much questions they want to entertain. But it's 20 minutes. And then I did kind of do a little bit of leeway in terms of trying to, we knew we were going to have technology difficulties. But I do appreciate everyone who's participating in the summit, anyone who's participating in the RFI process as we go through this. For those in the RFI process, today is the last day for questions. So please submit those to me so we can get responses back. And then submissions are due August 8th, so we can start reviewing those. Is there anything else you can think of?
Talk about August 8th.
Yep. Yeah, that was the last thing I just said.
I have one question.
Yes.
In your document, you said the submissions are due August 9th.
Oh, 9th?
Yeah. In your RFI.
Yes, thank you. August 9th. Good recovery, Scott. Thank you, Frank, for the clarification. Go with what is on the paper, not what I say.
Right.
I also say that this is left. So, yes, exactly. It's where I point and what the paper says, not what I say. All right, so with that, we're going to begin. So anyone who wants to stay on and listen, please do. Write things in the chat. I'll be monitoring that here as well. You have the mic. All right, we're going to try so we can start right on time in 5 minutes and see how it actually works.
Why am I recording it?
Oh, yeah. That is a good thing. So this is currently being recorded. All right, so who do we have up first? So Bill from Canby, you are up first. You want to try sharing your screen?
Yes. Hi there, Tracy. Yes, I'll try and share my screen now. Let's have a look.
Yeah, and for people in the room, you'll be able to see the person on the TV screen and the presentation on the projector.
Yeah, okay. There we go. Can you see this?
I have no clue. Yeah, we see like the slide
Lots
deck,
of
like all the
slides. Oopsie, sorry. Let's start from here, shall we? Okay.
Sweet. Yeah, if you want to try to. Oh.
Yeah, that's working.
All right. right, that's working.
That's excellent then.
All right, I do want to give everyone just like a few more minutes.
Mhm.
So that if they decide to join right at 8:45,
Okay.
they only miss a minute or two. I send them a little head schedule, which we may actually do, hopefully.
Mhm.
Bless you.
Mhm.
All right, good. So we have more people joining. Sorry, we're still getting some confirmation on technical stuff.
No. In about 4 minutes.
Yeah, I was just giving people extra time because the intro didn't take that long.
Yeah, the intro was on. You said that people were doing it and then force them to later on. You did tell people how people were doing it. And press the hell out of it.
Oh, but then we found out I'm wrong on the date, so it's actually the 9th.
So it's a good thing. We'll bring it out. And get ready to step in. That always good story. The left one first. Then I go with it. We're gonna do it after I actually do it after the show. Are you keeping notes of who's online, or should I look at that?
We should be able to.
Wish I could tell a stop.
I just noticed this. I thought there were like 2.
There's like 17 Scott Furmans.
I think the other.
The plan is coming together.
1, 2, 3, 4, 5, 6, 7, 8. 8 Scott Furmans have joined.
I think there are other people.
I noticed that, too.
And
We find one Scott Furman to be okay, but you know. Speak for yourself.
It's like YouTube if it only had cat videos. It's that awesome.
I can snip it and paste it.
Why is it showing up?
Why is what showing up?
It's all Scott Furmans.
I don't know. And say, is anyone on there that's listed under Scott
Oh, yeah.
Furman?
Yeah, this is Jeff. I've always wanted to be Scott Furman, so now I've reached that the pinnacle of my career.
All right, so Jeff who?
Jeff McBurney.
Oh. All right, any other Scott Furmans in there that are not the real Scott Furman? Please stand up.
He is standing.
This is Andre Brusso. I guess I'm Scott Furman as well.
Hey, Andre.
No, I'm Scott Furman.
This is
No,
Linda Dana. I'm
I'm
also
Scott
Scott
Furman.
Furman.
Tracy, my
Yeah.
name is Nick Rico. I'm not on the list, so I think I'm Scott as well.
All right. All right, I think I'm gonna put that in the chat. Okay. So is everyone getting my chats when I post it?
Yes.
Yes.
Sweet. Okay. All right. I'm gonna go ahead and do the post in the chat about, just type your name if you are Scott, so others know. So thank you all for calling out. And then I'm gonna let Bill from Canby go ahead and start.
Hi there. Thanks so much, Tracy, and thanks to all the Scott Furmans out there. Feels like I'm in the Matrix and everyone's Agent Smith. So thanks very much for the opportunity to present. Before I start, I'll just talk about who I am, and I represent Canby. I'm based in North America, in Pennsylvania. I've recently written a textbook on thermal hydrolysis from the International Water Association. I have a variety of different experiences, and my background is as a chemical engineer. So in terms of when we looked at the documents for PWD, we see a number of challenges. Obviously, there's no biosolids outlets in the state of Maine. With concerns about PFAS, there's a lot of stress on landfill, so you need material that's suitable for landfill. There are impacts on the surrounding communities. So the vast majority of material going to landfill and some material going out of state, perhaps to a variety of different outlets. But in terms of the solution, we believe the solution should be one which reduces the biosolids volume, because less volume you have, the less risk that you have. You want a high quality biosolids. By this, I mean low odor and desirable attributes. This increases flexibility for your outlets, gives you more options. You want something to be energy independent. Looking forward at climate change, every time we put on the news, there's some more extreme weather events. If we're independent of fossil fuels, especially for drying and thermal destruction, that's going to be a big thing in the future. And also, we want a biosolids which have a high dry solids, because as I'll describe later on, when we're looking at thermal destruction and PFAS removal, a high dry solids is key. Everything is in a water balance rather than in the biosolids balance. If it's high dry solids, it gives me options for landfills and also for thermal destruction. So before I go into more detail, the high figure number here, I would say for PWD, thermal hydrolysis and digestion will result in the production of 60% less volume of a high quality, low odor, marketable biosolids material with a high dry solids, which is appropriate for further thermal processing or landfill or whatever you want to do with it. So in terms of starting off with the technology update, so PWD can manage biosolids with confidence and ease today, whilst preparing for the unknown challenges tomorrow by implementing a no-risk solution. And we'll see this now with a technology overview. So for high level, what is thermal hydrolysis? Essentially, it's pressure cooking of sludge to above 280 degrees Fahrenheit, I would say, for a certain period of time, between 20 and 30 minutes, to change the properties of the sludge in a fundamental way. And the reason for doing this is it optimizes everything downstream. So with respect to PWD, I've shown you here two pictures of what commercially operating plants look like. This is the size of plant that you would be dealing with here. One of these is in Michigan, the other one is in Medina, in North America. So the pressure cooking, what does it do? It reduces the viscosity of your sludge, which means you have a thinner material. You can increase loading rate. I put, for example, co-digestion. I know there's an interest in merchant waste here, but it's not just increased digestion capacity, but increased drying capacity, increased capacity incineration in vessel composting systems, is increased capacity in anything downstream that you may have may be interested in. You're solubilizing your sludge. So if I heat something up, I solubilize it. This makes it more biodegradable, which ultimately means I'm going to have more biogas than, say, standard anaerobic digestion. I destroy something called ECP, extracellular polymers. This makes sludge more compressible. These are viscous materials which hold on to water. By destroying them and breaking them down, I can improve the dewaterability at a fundamental level. Means that belts work like centrifuges and I get much better dewaterability. And finally, I sterilize, which means I get no bacterial regrowth, minimal odors. I'm working now at temperatures which are significantly more than pasteurization. So what those mean is I have a lower volume of a higher quality material. If I can, going back to the left, if I can have a higher loading rates, I have lower capital cost. If I have more biogas, I have more revenue. If I have less cake, I have lower operating costs. And this is what we see at full scale. So why do thermal hydrolysis? There are a number of reasons why you would do thermal hydrolysis, but I'm going to focus on 4 of these in particular for Portland Water District. One is it's a good fit for municipalities with high costs of biosolids disposal or limitations for its end use. So in other words, where volume reduction is important, it's a good fit. It's also a good fit in projects where cities can establish some kind of a regional solids processing center, so you can gain from economies of scale. It's also a good fit where you need a high quality material. High quality material gives you flexibility for outlets, whether they're thermal, dried material, partially dried material, class A, low odor. It gives more flexibility there. And it's especially important in front of thermal systems where I'll show you later, you can improve efficiency and the energy balance. So principal components, I said, it's really a pressure cooking system, but it's in a number of stages. You need to thicken up first. So you have a pre-thickening stage. So maybe 16 to 18%. You can actually go slightly higher than this. So the cake that you have at the moment, this could be the starting point for thermal hydrolysis. The reason you thicken the material is to reduce the energy demand. Then you may or may not have storage, still at 16 to 80% solids. Then it's a 3-stage pressure cooking system where you add live steam by injection. This reduces the dry solids by about 2 percentage points on average. 330 degrees F for between 20 and 30 minutes. Then you have to dilute it down. And the reason for doing this is to control the nitrogen chemistry in the digester. Otherwise, you overload your digester. This dilution step takes out temperature, but it's still too hot to go in the digester. So we cool it down with a heat exchanger to about 104 degrees Fahrenheit. Feeding digesters typically at 10% solids, but that can range from about 8 or 9 with a lot of WAS. And there's one plant that feeds digesters at 14.5%. So looking at it at a slightly wider envelope here, you can see on the left-hand side, your pre-thickening. You have your heating and cooling, which I've just described. That's prior to digestion. Typically, most configurations are like this, but they don't have to be, as I'll explain. Then you have your final dewatering, and then your outlets, whether it's land or thermal processing or whatever. So in terms of the technology itself, there's a lot of plants. There's 84 plants currently, ranging everything in size from 5 to 450 dry tons per day. First plant was in operation 1995. They are in 26 different countries around the world. As you can see there, the vast majority are with land application, but there are systems combined with thermal processing, such as drying. There are systems with drying and incineration. There are plants with just incineration. There's even a plant with wet air oxidation, and there's an industrial plant with a gasifier downstream. But in terms of PWD, if you're looking at the size of your plants here, you'll be comforted to know that you're not alone here. So if you look at your current size, there are probably about 15 plants of a similar size, some of which are already operating in the US. You can see the future size, and with the merchant waste material that you're looking for, you're going to slightly bigger size. But needless to say, there are many, many plants of the size that we are talking about here today. So of those 84 plants, over half of them are repeat customers. So that gives you an idea of the complexity of the system. And in over 30 years of operation, with over 125 process trains, I'm not even talking about reactor vessels here, I'm talking about 125 trains. None have been intentionally out of service. Talking about service and maintenance, this is from Detroit here. They didn't do any maintenance for 2 years because of COVID. But when they did, they took it down for 1 week for the boiler plant and 1 week for the thermal hydrolysis. Again, this is the plant of the size that we'd be interested in here. And they used a landfill during shutdown. But their experience was they had a perception that it'd be a complex technology because it's a lot of stainless steel vessels. They found out it was actually the easiest part of all the new infrastructure that they put in. It's very easy to operate and maintain, a high availability, and they were especially happy with the commissioning service provided by Canby, where they got excellent support from the commissioning. So in terms of coming back to PWD, that we've seen about technology, but now I'm going to talk about the flexibility with this technology. So we're looking at flexibility in 3 areas. One is in the application of the technology. Secondly is in the types of products that can be made. And thirdly is in the type of contract execution that we can provide. So going on to there, if we look at the current scenario, let's say we're dewatering, maybe up to 20%, and it's mainly going to landfill with some out of state. And there's restrictions with PFAS we've seen in the regulations coming in. So there's an interest in thermal processing, such as drying, followed by some kind of thermal destruction. So I'm using your terminology here, scope 1 and scope 2. This is what the proposed solution is, looking at taking potentially your existing 20% cake, putting that through a thermal hydrolysis and digestion system, increasing the dewatability to about 32%. As I said before, 60% less cake, but 70% less water, because not only less volume, but higher dry solids, which means it's compatible with thermal destruction. You're now going to generate a low odor, high quality material, as I'll show you later on. You can also partially dry it, as I'll also mention, which can give you further options. So now we can look at the scope 2, where you would have some form of drying preceding some kind of thermal oxidation process. However, we don't have to start with that as a point. You can actually use thermal hydrolysis without digestion. So you can have a phased approach. So if you're looking at thermal hydrolysis with digestion, you can start with just the thermal hydrolysis. What's the benefit of that? Well, the benefit of that is the dewatering is significantly better. As I'll show, digestion actually deteriorates the dewatability when you have thermal hydrolysis. You're looking at percentage cake at least 50% here. You can go straight into drying. You can actually go straight into, say, a cement kiln, where you're going to get temperatures which exceed those required for PFAS destruction. So you can cut out your thermal destruction altogether. You're going to get 60% less cake even without digestion, with 80% less water. So your drying plant now, if you choose to go for drying, is between 1/4 and 1/5 of the size. So you can start with this and then add the digestion plant afterwards. Or you could have, like is becoming more of interest in Europe, in Central Europe, where there's no land application. You can have digestion first, followed by thermal hydrolysis. And in this case, the dewatability is improved, say 40% plus. And then this gives you compatibility with your drying and thermal destruction systems. So you can see this flexibility in where you add the technology. What I've done here is calculate the cake production. So the current cake estimation is about 42,000 wet tons. You can see using digestion by itself will reduce this by 1/3 or so. Adding thermal hydrolysis will reduce it by 60% with less water. This here, this fourth one here is digestion followed by thermal hydrolysis. And to complete the story is thermal hydrolysis by itself. And the reason this is important is if I have less volume, fewer transport movements, less material to go in your landfill, less material to thermally destroy, smaller drying plants with smaller water evaporation. And you have higher energy content now because you've got higher dry solids, which means you can put it into solid waste burners, you can put it into cement kilns, and you have less reliance on gas because you need less water evaporation. So in terms of the quality of the material, so there's flexibility now in the quality of the material. You can have a high quality cake. This is typical, which can go straight for land application by itself. You can have a very stackable material. Typically with thermal hydrolysis digestion, the storage requirements are less than 1/4 of digestion because less volume, it stacks at a higher stackable height. So you only need 1/4 of the volume. Low odor, nothing's zero odor, low odor with a different profile, typically earthy or like a burnt wood smell based on previous research. You can process it for sale to end users. You can partially dry it. And this is interesting because this gives you the benefits of a dried material, say at 90%, but only at 60%, which means I can use existing farming equipment, means I don't need a pelletizer. I don't have issues with dust. And it's not going to self-combust, if you will, in storage. So all the benefits of drying without the disbenefits, and I'm using much less gas. And also you have a much higher dry solids, as I've mentioned, so this makes it very good fit for thermal processes. So some pictures to see what that looks like. This is DC water, class B on the left, DC water class A on the right. You can see before and after thermal hydrolysis on the left and on the right. This is HRSD in the US. Basically, before they had some kind of like a slop. And this is even on the right. This is before they've optimized the dewaterability there. DC water, they've got a variety of different products there. You can cure it, you can partially cure it, you can add other materials into it to get different properties. This is an end user. They're turning the cake here into mulch, but you can see how high this is. This is about 9 foot high. So you're really not looking at a biosolids material here. This is a Thames water here. You can see the kind of material. It's actually taller than the walls of the storage area. So that's kind of flexibility with the material. Now it's flexibility with project delivery models. So with Canby, we can look at 3 specific things. Historically, it's all been about provision of shiny stainless steel equipment. So we can provide hardware, if you will, a proven technology with the commissioning and takeover testing. We can provide that. So that's on the one hand. If you go towards the right-hand side, we can take over operations of that plant. So we can give you performance guarantees and reliable uptime using Canby's expertise from other facilities. So we could take operations. And then moving further to the right-hand side, we're also getting more and more interested in financing projects, providing a source of capital. So in this instance, there would be an ongoing financial commitment where you'd pay for a service, where Canby would provide a service to treat, process, and find an end home for your biosolids. So moving from left to right, we see an increasing risk transfer from the owner to Canby. So there's flexibility in those options. An example of what that could look like here, you could see Portland Water District working in tandem with the owner's engineer. Canby would then work potentially with or slightly below or in connection with an engineering contractor in a special purpose vehicle. So essentially there's a single point of contact between the client and their engineer and the technology and service provider. So the contractor would be specifically looking at the capital project delivery, whereas Canby, as the core technology provider, will be able to give very robust guarantees based on know-how. Canby would be responsible for operations and maintenance, whether that's on-site or remotely, and also for the transportation and end use of the biosolids. So here's an example of what that could look like. So I'd like to finish today by going on to the dryness, because this is really key. You've got presentations later on drying, tomorrow on thermal oxidation. It's all about the water balance here. So what people don't usually realize is thermal hydrolysis has been around a long time before Canby has, and it was used as a dewatering aid. This is a paper from 1951. They found that if you use steam injection for half an hour, you're going to get around about 50% dry solids or higher. So that was the purpose. The original purpose was prior to thermal processing. This graph here shows the impact of various things on dewatability. So for raw, without digestion, you're going to dewater maybe 20-ish to 27, 28, depending on how much WAS you have and how much primary. So the more primary you have, the better the dewatering. Mesophilic digestion actually causes a slight reduction in the dewatability there. But thermal hydrolysis, as a rule of thumb, about 7 or 8 percentage points better dewatering than if you had digestion. If you put thermal hydrolysis downstream, then you're going to get maybe 38 to 48 percentage points. And if you have raw THP without digestion, you're going to get about 50% points higher. What people don't realize, the digestion process actually takes away 20 percentage points dewatability when you have thermal hydrolysis. So what that looks like, here's an example from a full-scale plant in Europe. There they were looking at a certain amount of biogas. They had drum drying downstream. The priority there was to put biogas to feed the dryer. In this instance, nearly 3/4 of the biogas was going into the dryer, you could see there. And they had a small amount of gas left over for other uses. They put thermal hydrolysis on half of the waste activated sludge. So they got a bit more gas because they were only processing half of the waste activated sludge. But you can see here the impact. You see here you have more biogas to begin with. The demand for the gas for the dryer was 40% lower because the dewatability went from 21 to 31 percentage points. So even though they only got 15, 16% more biogas, they actually had 2.5 times more gas left over for other uses. So what does this look like for PWD? Well, I've done the math here. I've looked at the current scenario, so 42,000 wet cake plus drying compared to digestion with drying, THP, digestion with drying, and digestion with THP and drying. So this looks at the overall energy balance. So if we look here, if we look at the light green, this is biogas production. So this is the energy content of the biogas that's produced on a daily basis. So as you can see, as you improve the digestion with thermal hydrolysis before and then thermal hydrolysis afterwards, I have additional more and more biogas. If you see here, the drying energy that you need is the red, the consumption of energy. With no digestion, I have the most amount of material to dry, so that's the highest drying energy. With digestion, you see here, this is smaller because I've converted some sludge into biogas. But now with thermal hydrolysis, with improved VS destruction and improved dewatability, you can see here my drying needs are significantly lower. And they're lower again if I put THP downstream. So now if I'm looking at the energy for thermal hydrolysis, it's this kind of teal color. But what we can see is as we move from left to right, the more thermal hydrolysis I put in, the better the energy balance. And even with accounting for the energy of thermal hydrolysis and drying, I could be dependent on fossil fuel energy moving into the future. And this is a very important point here. So I'd like to finish. I'd like you to thank you for your time by saying that PWD can manage biosolids with confidence and ease today whilst preparing for tomorrow by implementing a no-risk solution We've seen no risk solution with over 80 facilities worldwide running over 30 years, with half of those are repeat clients, with extremely high availability. You can have flexibility in terms of how you implement the technology, reducing the volume of the biosolids producing different types of biosolids, which you can do different things with, and being energy independent moving forward. And you can be scalable and adaptable for future concerns such as PFAS and other emerging contaminants. You can have a drier material, which means you need less energy for your dryer. You can put it in a cement kiln even. So you can do all sorts of things by doing thermal hydrolysis. So with that, I'd like to thank you for your time and take any questions if there are any. Thank you.
Thank you, Bill. We have an echo. So,
I have excuse me.
thank you, Bill Scott. Okay, we unfortunately don't have time for questions. Sorry, Mac. Do you want to take Bill's information? Make sure we can get that to you so you can ask that.
Yeah, I'd like to say if anyone has questions, please feel free to reach out at the email at the bottom of this slide. And, you know, we can make a copy of the presentation slides available if you want to have a closer look at the numbers and have time to go through it and find questions.
Perfect.
Please feel free to reach out. Absolutely.
Yeah,
And thanks very much
that.
for your time.
Bill, if you would kind of just keep on. So I think Mac is going to type it in the chat.
Yes, Scott Furman.
As Scott
course, yeah,
Furman. If
I
you wouldn't
can
mind
stay.
responding, that would be wonderful.
Yeah,
And
I can
Jim,
stay
if
on
you
the
wanna
chat. Absolutely.
Yep. So that you can start your presentation.
Mhm.
Yeah, and anyone who is here who has a question and we don't have time, kind of flag me or something, because I can bring you my computer or you can use Scott and we can type it in the chat. Yeah, so we'll do that. So Jim, are you
Morning.
all set to share?
I think so. Yeah. Oh.
Number of respondents that we had, potential presenters. Trying to keep this to 2 days. This is basically fire hose and shotgun technology introduction.
All right, so Jim, whenever you want to share and begin.
Okay. I am attempting to share. Let's see. There we go.
And this is why I build in a little bit of extra time, hopefully.
Okay, so you see what we've got here?
Yep, perfect.
Okay. So let me get it back up to the start. So I'm Jim Grumman. I'm the group leader for Varic Biogas and the Ovivo Biosolids Management and Resource Recovery Team. And what I'm going to talk about today is basically just an overview of what we can offer. One of the things about Ovivo is that we have a lot of different technologies for biosolids management. And so I'm just going to highlight a few of our more prominent ones. So this is just showing a typical activated sludge process, you know, primary clarifier through a biological reactor and secondary clarification, then your WAS into your thickener, and the thickened WAS into your biosolids processing, which primarily it sounds like you will probably be going to anaerobic digestion would probably be the most efficient option for you. We do also offer equipment in the aerobic digestion sphere here. So Ovivo, as part of the biosolids group, has sludge conditioning with thermal hydrolysis, as well as algal hydrolysis using algae. As far as the digesters go, we have mixing, gas storage, and digester covers. Solid stream nutrient removal. So this is post the anaerobic digester. We have post aerobic digestion for nitrogen and ammonia removal, and we have ELOVAC system for the phosphorus removal, which I'll talk about a little later. We do not offer a dewatering technology. There are plenty of fine ones out there now, but we also offer deammonification and phosphorus removal in the side stream. So we offer both in solid stream and in the side stream. And then as part of the Ovivo group and part of my group, we also have biogas handling. So for safe transport and utilization of the biogas, including the flares, equipment on top of the digesters, gas cleaning and drying if you want to go to a CHP set, and also gas upgrading for RNG systems. So first thing I'm going to talk about is the sludge conditioning. Very good presentation from Camby on thermal hydrolysis. I will just discuss our process a little bit. Primary difference between this process and the Camby process is that we use heat exchanger to do the hydrolysis, and of course you get all the same benefits, volatile solids reduction plus improved dewaterability, and that leads to lower hauling costs. Also, you have the increase in biogas yield, quality of the biosolids is increased, and you can improve your digester capacity, lower your HRT and your viscosity. So this shows the lysotherm process, process developed by our sister company in Europe, a company called Eloquo. And so basically we use a thermal fluid to sludge heat exchanger, preheat the sludge, goes through the high temperature heating for the lysis, and then through a reactor, high temperature reactor, and then we offer a cooling stage. So the advantage of this is it is a very compact system comparatively. We don't need to thicken the sludge prior to going through the hydrolysis, and we don't need to dilute it to cool it off before going into the digester. Okay, so this is going to move pretty quickly because 20 minutes is not a lot of time, but okay, so next thing I'm going to talk about is the digestion equipment. I'm going to talk specifically about the linear motion mixer. The linear motion mixer is a low energy digester mixer. Primary advantages to this is it gets around a lot of the problems you have with poor or insufficient mixing of the digesters. Of course, if the digester is not mixed properly, it's going to affect your retention time, your biosolids quality, and the amount of gas production. So these are just some typical problems that are seen in poorly mixed digesters with grit accumulation, stratification, and short circuiting. So the linear motion mixer, it is as simple as it looks. It's basically a hydro disc which moves up and down. You have a Scotch yoke and a drive mechanism attached to that. This moves up and down and provides a very thorough mixing of the system, but very low energy. One of the key things about the low energy mixing is that it also has less possibility of rapid rise events or foaming problems in the digester because you're not imparting a bunch of energy to the sludge. You're just basically providing enough energy to mix it. And as far as this project goes, as far as your biosolids goes, what you're going to be looking for besides just the biosolids disposal is probably going towards a net neutral type plant. You want to, make sure that you're utilizing your biogas as well as not going with any extra energy. And so these LM mixers are, as far as the amount of energy used compared to other types like chopper pumps or jet mixing or draft tubes, your energy usage can be up to 10 times less. So that helps you reach net neutrality. This shows a case study versus draft tube mixers. So on this particular digester, there were 1 center and 4 external draft tubes, total nameplate power of about 90 horsepower. And with the LM mixers, we were able to provide the same mixing capacity with 1 mixer that had a total nameplate power of 10 horsepower. Okay, so I'm going to move on to biogas handling. Again, Varick Biogas was purchased by Ovivo 4 years ago. We've been in the industry for over 70 years. And so, as you can see from this slide here, we make a complete line of equipment from flares on the left side, or on the right side here, to pressure vacuum relief valves and things on top of the digester cover. So this just shows the types of flares we have. We have both open type flares or candlestick flares as well as enclosed flares. The enclosed flares are normally used to provide a flare where you're not seeing the flame, as well as with an enclosed flare, you're able to meet lower emission standards. So you're getting above 99% destruction of the methane within the flare, as well as low CO and NOx emissions. This just shows a typical system with digester gas cleaning. We have a number of different technologies for hydrogen sulfide removal. Sorry, there's an animation here that keeps going. So you have hydrogen sulfide removal into moisture removal. Moisture removal using a chiller with a couple heat exchangers to lower the temperature of the gas and then raise it back up. And then siloxane removal, either using a temperature swing absorption system or granular activated carbon. And this shows the regenerable siloxane removal system. This is similar to a system that that Brown and Caldwell just did at Dairy Township. So basically, it is a specially designed polymer that's designed to remove the H2S, or to remove the siloxanes. And then this shows it also that you can you have 1 tank that's in service, as well as 1 tank that is being regenerated. And so that saves you a ton of money on carbon costs. Sorry for the move around on the slides here. So this shows a typical gas upgrading system. So you have the H2S removal system, blowers, moisture removal, going through the siloxane removal, and then the added step of CO2 removal using membranes. Okay, last thing I'm going to talk about, well, the 2 last things I'm going to talk about are side stream nutrient removal. Our side stream ammonia removal system is called Animopac. So this is the oldest Animox-based system. in the world with the most treated capacity in the world. And basically how this differs from some other technologies you might hear about later on in the day is that we use a granular system. Hold on, can you still see my slide? I'm trying to stop these animations.
Nope,
Okay,
you stopped for sharing.
okay. Let's see. Okay, sorry about that.
It's all good. We're all dealing with technology today.
Okay. So the difference between our technology versus other technologies is that we use a granular based system. Basically, the granules can contain both the ammonia oxidating bacteria as well as the anammox bacteria for nitration and denitration. The key things about this is that it provides a much smaller footprint as well as a much lower capital expenditure to as far as the equipment as well as the civil, and it has no moving parts, and you're actually recovering the anammox bacteria, and you can sell that as a product to plants as that go through either an upset or into new plants for seeding. So you can see the footprint versus conventional denite
And
system.
we still can't see your screen.
Oh, okay. How about now?
Yep.
Okay. So again, the nitrification, denitrification system, it's all granular based, and you can see the footprint of the animal pack system versus conventional denite systems, and versus competing deammonification systems that typically use some sort of media to grow the bacteria on. So again, this shows some of the benefits. This shows the energy consumption, so it has a much lower energy consumption than conventional, and also versus competing type systems. And then startup time is one of the critical things. Many of the media-based anammox-based systems, can take anywhere from 6 to 8 months for startup, whereas we can start up in less than a month. And in fact, in some cases, we did a startup in the city of Fond du Lac, Wisconsin, when the temperature was below zero, and we were able to start up the system in 1 week. So. Okay, so last thing I'm going to talk about today is oops, sorry, I meant to. Okay, so this just shows that we also have a phosphorus removal system for the side stream that goes along well with the animal pack, and it allows you to remove and harvest struvite from the system in conjunction with the anammox nitrogen removal. As a standalone system, I'm going to show you the solid stream version of this, and this is a solid stream nitrogen removal. It's post aerobic digestion. It was developed by DC Water and Dr. Novak at Virginia Tech. So this is basically an aerobic digester that goes after the anaerobic digester. It provides a very simple system for nitrogen removal, using digested organics for the carbon source with no chemical addition. And it operates just like an aerobic digester. You get increased volatile solids destruction, which improves your dewaterability, struvite stabilization, so you don't have that dropping out in your system, and also provides odor reduction. So last thing I'm going to talk about is a system we have called Elovac, which is a solid stream phosphorus removal system. So in the Elovac, we are providing a phosphorus removal system that is not a struvite harvesting system. It is a struvite precipitation system. And by precipitating the struvite out into the solids, you increase your dewaterability. So you're not binding up the water in the phosphorus. And this has a much smaller cost and a much smaller footprint than a harvesting type system. And we feel it has a lot of advantages besides just the footprint and the lower energy cost. You know, there really right now in the US, there is not a very large market for struvite sales. In Europe, it does well as selling it for fertilizer, but to be honest, it's not a real marketable product right now. So by binding it up in your biosolids and preventing the moisture from binding with the phosphorus, you prevent your struvite scaling as well as increase your dewaterability. Our system that we have, basically it just works by, it provides a vacuum on the sludge. So this is post-digestion, small amount of magnesium chloride added in, digested biosolids, and then we create a vacuum. And what that does is that, first off, it draws out all the biogas. So you're able to put that biogas back into your system. And by drawing out the biogas and the CO2, you're raising the pH of the biosolids, and you're raising it to the point where, you know, phosphorus drops out at about 7.8 pH. Struvite drops out at about 8. So,
For my presentation.
and we've got a number of
Glad you're laughing.
number of systems in Europe. We are manufacturing in the US, and currently we're building a system to replace a pilot system that is at Provo, Utah. And last slide here is just showing all the different technologies that we have and our capabilities within the whole biosolid sphere. So, and that's it.
Great, thank you. So we have a minute or so left for any questions. If there's any. Let's see if there's any in the chat. Nothing's come through here. So thank you, Jim. I know you went through a lot of information. Vivo does a lot of different types of process. Do you wanna, people in this room, we can definitely get you Jim's contact information if you didn't get that.
And
just
also,
talk to Rob.
yeah, Rob Trepaz is our local representative, and he's also able to answer any questions that you may have later on if you catch him during a break or something.
Exactly, yeah. So Rob's right there. So just if you have questions for BioVivo, please see him and he can get the information.
You want to mention Scott Furman, can state their name by clicking on.
Yes, thank you. If you are currently listed as Scott Furman, you can change your name so that we can see who's here. you would click on your name, there should be like 3 dots and you can rename yourself. And
Don't
if,
rename yourself Scott Furman.
yes, please. If you are not currently presenting, please put yourself on mute so that we don't hear any background noise or conversations that are occurring. I don't have a way to just mute yourself. Jim, if you want to tee up, so Jim Dunbar from Listech, if you want to tee yourself up and start presenting. Or yeah, start sharing. And
All
then
right.
1 second. All right. Jim, you are good to start.
All right, I assume my screen is up.
Yes, it is.
Great. Fascinating to still be on schedule. Congratulations to the previous presenters. Again, welcome here to talk a little bit about Listech International and our technology. Myself, Jim Dunbar, currently the general manager, business development manager for Listech in the United States. Over 25 years in the business of solid waste and liquid wastes, treating in North America and Europe. Contact information is there, which will be shared. So a little bit background on Listech, 25, coming up on being a 25-year company, founded by a few industrial microbiologists up in Waterloo, Canada. Leading and largest THP process in North America, patented process. Those first years with the company, first 6 or 7 years, were totally dedicated to research and development. As was spoken to from the previous speakers, THP has been around for a long time. What the founders of Listech were looking for was to really bring it to the masses, make it much more readily available, easier to operate. And I'd say the last 15 years have been a success of that philosophy. And what they really wanted to focus on was using those inherent features of biosolids that have been available to us for generations. Never really, as an industry, looked at it that way. We always looked at biosolids as being a waste product, not a feedstock product. We always looked at biosolids as something at the back end that had no real purpose or use. Listech's goal was to take that as a starting point and to provide opportunities for increased value, increased benefits, and really maybe a more holistic approach. We believe in reuse and beneficial use and less on the destruction methodology of some of the more current technologies, but every technology has its place. So we've already heard a little bit about the THP technology. I'm going to go a little bit into the Listech THP version. It is a smaller, compact system. It is a low temperature, low pressure, no pressure, basically, reactor vessels. Our temperatures are at the 70 to 75 degrees Celsius range, about 160 degrees Fahrenheit. We operate under kind of a continuous batch mode. Our reactors process about 3 to 4 tons of dewatered cake material on a cycling basis. We provide high-speed shearing, which is the mechanical portion of breaking open those cells. And we have an alkali to pH adjustment to make the cell walls more amenable to destruction. And all of that happens concurrently in these modules. Our alkali can be a variety of products. And I'll talk a little bit more about the benefits of using a couple of them over others. But we typically will bring the pH up to a mid to high 8 range. And again, that is a very short-term parameter that's used. Once it's processed, we find within 15 to 30 days, the pH normalizes back down to somewhere between 7.2, 7.4. This is a low energy technology, does not use, like I said, we don't require a lot of heat. We don't require a lot of electricity to make it work. And at the end of the day, what we have is really a multi-purpose products. The traditional product that we've always marketed our company on is List2Grow, which is a beneficial use fertilizer. But we also I'll be talking also about List2Mise, which is a anaerobic digestion optimization product, and then List2Carb, which is more of a nutrient removal technology. All of them are produced in the same technology with slight different variations, which I'll be going a little bit into. And just as the sake of scale, these modules do tend to be about the size of a good wine vat. They're anywhere from 12 to 15 feet tall and anywhere from 8 to 9 foot in diameter. So not a very huge footprint to construct these, and they are modular. They can be put in parallel to accommodate different sizes of operations. Pictorially, here's kind of what they look like. The one in the middle is a typical reactor with the superstructure built around it. Very clean. Everything is inherent in the material. The left-hand side shows what the shearing blade looks like on the inside. It is basically a high-speed cutting wheel. This operates at about 400 to 500 revolutions per minute. It is a very aggressive environment in these reactors. We try to when we use the energy, we want the energy to transfer itself into the actual product, hence the shearing mechanism. And then over on the far right bottom is kind of our dispersing motors that sit on top of the reactors. Each reactor operates independently of each other. And like I said before, they can be put in parallel to increase operating capacity. So we full service staff in-house to provide the process engineering behind all these. A few pictures of the reactors along the bottom there. Again, they're very standalone, we'd like to consider them very clean systems. The typical operation would go at the back end of an ongoing treatment plant. So where treatment plants don't have plans for expansion or upgrades or modifications, we fit nicely at the back end of an anaerobic digestion process without really any change at all to the current wastewater plant operation. If a wastewater plant is going through significant upgrades, these can be really tailored to fit in to any design criteria, any design pattern that the wastewater plant is going to. You can see on the right, it is fully SCADA operable. Our systems tend to be very highly automated, where operators tend to be more overseers of the process. Once the system is turned on, it basically self-regulates itself with the dosing, with the speed of processing, and the movement of material through instrumentation, temperature, pressures in pipelines to make sure we don't overpressurize, temperatures for stability, and then level sensors within the reactor itself. These SCADA systems can be integrated into existing SCADA systems so that existing staff can easily operate the system really without any additional personnel, or they can be managed as an entirely separate function at a wastewater treatment plant. We provide that integration. We also provide remote access. Our engineering support team provides ongoing capability to be reached out to help diagnose any ongoing problems if there are any. We also provide the ability to audit these systems with staff just to make sure as we progress through improvements, we can bring those to existing systems that are already in place. So a little bit of where we currently stand in the field of THP. We have a few large regional centers, and these are merchant plants, one in the Toronto area and one in the San Francisco Bay Area where I'm located. We also have 10 in-plant deployments. These are our single-purpose operations dedicated only to the treatment plants that we currently support in the biosolids management field. We also have one third-party regional processor. We also have a handful of plants in design and construction. We currently have over 19 modules in service and operation. All of them are at full scale, commercial, like I mentioned before. Those early years of research and development, we did at our behalf, not at the client's behalf. So we provide really a high proven technology basis to go by. And I mentioned on these merchant plants, we service currently over 60 individual generators, both wastewater treatment plants and other organic residual producers. That would be food and beverage waste industry that have either managed organics that still need further management, either due to regulation or the desire to take high strength waste, either through the process or directly into the LISTEC process. So a brief overview of some of our larger merchant plants. These are the two I spoke of before. The one near Toronto in Ontario, Canada, has been in full service operation for 11 years now. The one in Fairfield, California, going on 7 years past. Both of these manage multiple source materials. I can speak very clearly about the San Francisco operation. We currently handle biosolids from over 12 different wastewater plants, including food and beverage industries that are in our area that are looking for reliable and beneficial use outlets. We deal both with dewatered cake, and we also have liquid wastewater streams that also need processing, and all that helps combine our standard recipe that we like to be in that 15% end product range, which allows us to take in a variety of products at variable solid contents and basically blend them and either dilute them or thicken them to our desired end process. And both of these, I said, they're standalone facilities, wholly constructed and financed by LISTEC with contracts for incoming material. I want to get into the list to grow process. This is where I think we've made our mark in the industry. We're not an equipment sales company per se, where we do have merchant plants that we own and operate. We also provide, obviously, the back end sales and marketing of the end product fertilizer. For those plants where our technology is implemented at a wastewater treatment plant, we also provide market and sales support to the client on an ongoing basis, multi-year, with the goal of being, if we're going to make a product, we want to make sure that there's an outlet for it. This has not been any problem in moving material for land application. And I know in Maine, given the current status of land application of biosolids, we've been able to not circumvent, but we've been able to basically go higher and above that by getting our product basically certified and graded as a commercial fertilizer. So in California, the Department of Food and Agriculture has licensed us as a commercial fertilizer.
Hey, that's a rhetorical question. Doing well. I'm doing well. I hope the same for you on a beautiful day. Yeah, we had it's all positive.
Everyone please mute themselves.
Take part home from the outside.
Sorry.
And it's
Can you
like
please mute
45,
yourself?
6 years old. You're gonna find things. So we are rebuilding houses.
Yeah, I don't know.
All right. Sorry about that. Getting back into the fertilization process. Like I said, in California, we worked with the regulators to have our product classified and licensed as a commercial fertilizer, which has allowed us to move it out of the traditional biosolids call it definition or classification. And so we land apply in areas where traditional Class B biosolids have been either banned or heavily restricted. And we're basically a full service provider of that material. And I think that that's an important distinction if we're looking to still get the higher and best use. What we feel for biosolids is maintaining its status as a nutrient-rich material that historically has been an agricultural component for many areas. And to speak specifically of the PFAS issue, while PFAS is certainly an ongoing discussion in almost all quarters, with the highlights being, we don't have a number yet. We don't have a number that quantifies where PFAS is going to land in the regulatory framework. We do know that EPA is looking at designating, PFAS as a hazardous substance. And while that, should scare many of us, the current circular or Superfund legislation actually already provides liability relief for hazardous materials in the normal use of a fertilizer product. So we've taken this definition to heart by basically saying, if you make a manufactured fertilizer product, as there are many on the market that have, hazardous materials and compounds in them, as PFAS will probably be designated as such, Superfund liability is not applicable when it's used as a normal fertilizer. So we really look at this as a double approach by saying, yes, we're going to make a commercial fertilizer not only to go higher and above than any type of bans, whether it's statewide, countywide, but also from a liability standpoint, that we are treated no differently than any of the commercial fertilizers that are manufactured on the marketplace. And we feel this is a very, very strong motivation to keep biosolids, at least, in certain quarters of the country, as its traditional method of end use, which is basically, a soil additive for agricultural purposes. Briefly talking about our optimization program, the list of MIs, again, same product, slightly different recipe. And what I mean by that is where Listagrow is a product that leaves the facility, hence needing the Class A designation and higher nutrients. When it's kept on site, recirculated back into anaerobic digestion to allow the bugs in the digester have a second bite at the apple, so to speak. We really don't need to produce a Class A material. We're just looking at very highly hydrolyzed material, basically increasing the soluble COD component. We have a full-scale commercial operation going down in Southern California. We feed 100% of the TWAS material back into anaerobic digestion, and resulting gas is at 20 to 22% increase. And then for every percent increase of gas increase, you get a corresponding increase or decrease in biosolids at the back end. So that has been a success that we're very proud. We'll be providing that in future presentations within the next months of the year at conferences. So what we do see as we approach looking at wastewater treatment plants that are currently, struggling with ongoing issues of, higher costs of end product management, and typically whether it's a liquid program or a solid program, the challenges of where is the end product going to go. I mean, anaerobic digestion is an excellent technology for wastewater treatment plants. However, to take that to the further step of what now do you do with that cake, where restrictions have been coming at us at all sides, what we are basically looking at is, well, let's make something better than just what we've always done in the past. So where landfills and land application have been those traditional outlets, as those have been squeezed, other opportunities provide themselves. Hence, with a higher product technology and a higher product standard or qualification, classification, we've been successfully able to move our product into areas that maybe haven't been so easy to get into in the past. And that's our staff effort. We have agronomists and certified crop advisors on staff to do that work at a local scale. So We certainly look at THP as a very viable and proven solution, as we've seen from not only our company, but others. It's been around a long time. Listec also has been around a long time, whether we get our name out there as maybe others have. We have been growing very successfully over the last 14 years. Every one of our operations still in business, still at commercial scale, and still providing beneficial use services to our clients. And with that, fortunately, I can leave a few minutes for questions if needed.
Great, thank you, Jim. Is there anyone here that has a question or online?
Are you at the current time still taking most of your material out as a slurry? At one time that I seem to remember that's what Listec was doing. What is the typical solids of your product?
Our end product tends to be between 14 and 15% solids. It is a liquid. The viscosity ranges from 5,000 to 10,000 centipods, so it's a very pumpable product. In storage, it will stay in its colloidal physical state for years. There's no physical separation. The solids themselves do not separate out. It's inherent in the material. There is no free liquids that come off of it. Like I said, it'll stay in product suspension for many years. Not that we wanted to. We have sample jars that are many years old, but the product itself moves kind of, quote, off the shelf very quickly during land application season around the country. So if nothing, thank you very much for your time. Look forward to give back a few minutes of upcoming break.
Great, thank you,
Thanks,
Jim.
Tracy.
Appreciate your time. All right, so we are at a break. So we'll be back here starting promptly at 10 a.m. Eastern time. So I gotta say AM because I don't trust Scott. He'll be like, oh, you said 10. PM. And then we'll start with the lip tank system. So thank you, everybody.
Yeah, are we coming back at 10 or 10:15? It's 10:15.
Oh, sorry, 10:15.
That's why I was confused, not AM, PM.
Yeah, 4 minutes. No, so what are those? 10:15. I just saw the first one. And we'll start at 10:15. We'll do this. I'll share.
So well, you look at my yeah, there you go. Oh, yeah. I get that. Although usually I do my own guilt. Or my own problem. Yeah, no. I heard everything I had that film. Yes. Yeah. I think it has to do, there was a small portion of the road.
Yeah, that's what I got.
Feel free to,
So once I let you know, I. What did I say? Don't do what I say.
I'm good, how are you?
Yeah. Yes, sidewalk, someone for tax.
Yeah, you can mark ourselves a little bit better. Yeah.
Yes.
But it really is almost. I don't think you have to get involved in the. Right.
Yeah. Well, and you're right.
Yeah. Just maybe. Well, no, I mean, I was. Well, I knew it, but you know, you find out. I have. You got it.
But I never even thought about it.
Yeah, yeah, exactly. I didn't mind that hands-on stuff. But working with my very more like I don't know. I think it's hard to make like how do you organize and go that everything of what we talked about.
Like our offices, where I was involved, so we are day to day with the.
This is.
So you get it back, I'll catch you up on it. Yes. That's one thing I can never look for. I've seen it from here. All right. When we were at the well, I know. Yeah. Old enough. Yeah. Oh, yeah. Well, if you. It's not what I thought. I have no right to move. I have no rights All right, 2-minute warning.
Good morning, Tracy.
Good morning.
How are you today?
Good, how are you?
Hey, I'm getting organized here. I got on the system. Now, when I go to share, I just hit share the screen on the bottom and that should pop up.
Yep. Yeah, if you want to go ahead and pull up, we're gonna start in 2 minutes.
Let me see if this works. Hang on.
Yep,
Does that show up?
yep, I can see you perfectly fine.
Oh, wow. It's amazing. Technology is working. Good deal.
Yeah, so if you want to just leave it up. And
Yeah,
then,
if it's okay. I just leave it on the screen. Does that work?
yep, no, that's perfect.
Great. Thank you.
And then we'll start in 1 more minute.
Okay.
But they still said this is a bad idea. Well, I mean.
That was cycling through nicely.
Good. Okay. Well, it's going to work fine. Thank you.
By the time you guys sit down.
I don't know. I'm so I find these sunglasses in the mall ones. My head, they were kind of like crooked. And the gentleman at the booth said, I think it's your head. Maybe it'll
Alright.
one of the other Scott Furmans.
If everyone on the computer can put themselves to mute.
I don't think like that one
So you're telling me it's my ass? I don't know. I just tell a story.
It's lined up for, yeah, I mean, just about a moment to that. Yeah, just covers the top.
All right. Al, if you want to go ahead and start going.
Okay, great. Good morning, everyone. I'll introduce myself. My name is Al Lettinga. I'm with the Lip America Tank Systems organization. And I'm the National Marketing Director for that organization. Happy to join you this morning. We're the North American company for the lip systems and the anaerobic digestion systems that we offer. Our offices are here in the Metro Detroit area, specifically Novi, just outside of Detroit. We at Lip America, we operate, complete design, manufacturing, assembly of the digester package systems, as we call them. We'll show you, I'm going to show you today some different digester packages that we offer. We provide budgeting, engineering, installation completely from the specific design of the digester all the way till operation and getting the operation, the digester moving forward with the gas distribution. This morning, I'd like to run through some different packages on my PowerPoint and show you what the lip system is and what we offer, and a little bit about how the lip system is constructed. So with that, we go to our next slide. Lip is a German company. Our parent company is out of Germany, just a little bit west of Munich. Family owned, third generation. We're working now under the management of the grandson of the original designer of this system. Mr. Lip Senior provided over 170 patents, several of which are the double seam system. They also have a welding technology, and we have a very unique manufacturing system as to how our tanks are built. More than 30,000 projects around the world. So it's done very well. And these are some of this slide simply shows a few on the right of the digesters that we have in place. And we're going to talk about 4 different digesters. As we see on the left, our digesters are named this way. You know, we use terminology. The one up on the top is called a combioreactor. The flat roof system in the center is called a universal digester. The two tanks down below are actually located. I know that in the room or for presentations you have Canby listed. This is at a Canby plant in Central Ohio. Those are two 800,000 gallon echo digesters. And then we also have what we call a unicentral mix system that we'll talk about. The LIP system is not only digesters. We provide wastewater tanks, energy systems, heat storage, gas storage tanks, you know, different types of silos and bulk storage as well, along with our roofs, you know, pumping, floor mixing, insulation and cladding, all our PRVs and safety equipment that we provide in our tanks. And so we also can get into potable water, but that's not what we're focusing on today. Today is predominantly around the anaerobic digestion process. This slide simply a little bit repetitive. It just simply shows a little bit of the different tanks that we offer. We do actually offer a gas storage tank, and I've been working in a lot of areas with gas storage, simply a steel shell with an internal bag for gas collection. Of course, you know, typically liquid storage tanks are available as well. So with that, we'll look at a few more pictures here: waste treatment, digestion, bioenergy. And with this slide, I'd like to talk a little bit about the actual double seam system. That's that's a very unique and one of a kind, the only type of system in the world that's operated this way, in which we build a tank. We build a tank with a coiling system. It's actually two set up machines inside the ring of the tank on the site. This machine and this bending and folding process takes place on the job site. So the coils are delivered to the job site and set on the concrete pad, and the double seam system begins to uncoil. A typical tank could take as short as a week and as long as 30 days to build. We build tanks, you know, anywhere from 10 feet in diameter, well over up to 160 foot in diameter. The thickness is on a metric basis, 1.5 millimeters to 4 millimeters thick. The coil itself, that's the thickness based on the location of the coil in the tank wall. The volume of these tanks, 25,000 gallons at the beginning, but we can go up as high as 3 million gallons in our tanks. The depiction on the right simply shows a bit of a idea of how the fold takes place. There are two machines, as I said. The first would make the break at the beginning, coil, and as the coil comes through the machine, it breaks it, it curls it, and then the final machine would be where it brings the two pieces of steel together into a double fold. The blue dot is simply some sealant that's put in the center of the fold as simply a secondary sealant around the edges. So and we will fold. Our uniqueness of this is what's called a Varanox system, which is a two-party or two-plate system. It's externally galvanized plate, and internal it's stainless steel. So what we have is, again, showing the picture of the machine in the left, and on the upper right, the coils are coming around. He's simply marking the location. Down in the bottom left is a depiction of how this folding process and the double plating is depicted. We have the darker layer is the outer galvanized plate. The inner layer is the stainless steel, typically 316 for digestion. And we have a internal separation layer of an adhesive material that is operating as a separation. So we do not have dissimilar metals within the tank structure on the inside, which would for us eliminates cathodic protection, any type of anode problem. So our tanks do not require cathodic protection as many carbon steel tanks would. The tank assembly process down in the bottom left, it shows how the coils are unrolled, and it rolls. The tank actually spins. The machines are fixed, they stay in place, and the tank shell itself spins upward. as the coils are unwound out of the frame through the machine. And it's, again, as I say, it's a very unique process. It's very quick. It goes up fast. We spin these tanks up, and then we begin to assemble as it goes up the fittings and such. And we'll see some pictures as we go along. Today, we're going to, just for the short time that I have you, we're going to talk about, or try to get through as quickly as I can, 4 different digesters. We have the Combio, the Universal, the Unicentral, and the Echo. Each one is unique, somewhat unique, although a lot of the features are the same as far as our lip digesters are concerned. We have a mixing process, we have heating, we have heating coiling, we insulate our tanks, and we have our level controls are all affixed to the sidewall of the tank as a package. This slide again depicts the same, but a little more detail. Our operating pressures can go from 8 inches to 10 inches in these 3. They can go down as low. I mean, the European model typically is a low pressure system. Yeah, for the most part. In the US, we get involved a lot of times in discussing the whole pressure issue in regards to fixing roof systems to allow for pressure. The three systems that you see in this slide, the Combio, Universal, and Echo, are what I would call a mid-range pressure operation. 2 to 3 inches up to 10 inches approximately in those systems. If we want to go to a higher pressure system, we would go over to the lip Unicentral mix system, which I'll discuss how that operation is put together in regards to the tank roof system, which is where the majority of the issues come up to when it comes to pressures. Going back over to the left, the Combio system, and we'll talk about each one of those. This is what we call a package plant. It's all encompassing. The bag is up under the hood of the sloped roof. And this particular tank system, it maxes out at about 800,000 gallons in capacity with a gas storage of about 600 cubic meters. The center digester, the Universal digesters you see, it maxes out about 1.8 million to 2 million gallons. It has a flat roof, a flat stainless steel clear span roof. And again, it's a low pressure system, lower pressure. Again, all of these tanks, digesters that we have are provided with mixers as well. And the Echo system is set up with a gas bag on the top, a DMR, a dual membrane cover. We can go upwards of 2.8 to 3 million gallons in those tanks. Much higher pressures can exceed 10 inches water column. The gas bag can be either like a quarter sphere or up to a half sphere in regards to capturing the gas on top of the tank for distribution. Then we move over to the Unicentral mix, where we actually have a 2-part roof system, and this allows for the mixer to be placed at the top of the tank for a center stem mixer system. In the case of digesters, that would be designed around a center mix system. This also allows for a much higher pressure, up to upwards of 14, 16, even 18 inches water column pressure system, based on the fact that this tank has a 2-part roof system, which allows for an external beam to support the mixer. And we'll also see some pictures of that as we move along. Starting out here with the Combio, I'll just go through each one of these digesters and give you a little detail of each one as we move along. Again, we max out at about 800,000 gallons of total capacity. We have a side mix system. These, as you can see in the right picture, cutaway, the bag is in the top section of the digester, and the cover sloped like a 30 to 35 degree sloped roof system, protects the cover from UV rays and gives it a long-lasting operation for the gas bag itself. This particular system is a very low pressure, somewhere around 1 to 2 inches water column, and it operates as a package, mixing, heating. We have the overflow system included, and then we simply have our PRV and sight glass and all the accessories attached as a package system. A little better cutaway of this particular tank. shows how about a third of the, about 2/3 of the tank is digestion, is the liquid level. Above that, we have a headspace, and then we have our gas storage above that. P&ID would give you a little better idea of how this detail is laid out. We also provide what we call a drop shaft on the sidewall internally. This allows the substrate to come in at the top of that drop shaft and then pull out through the bottom and agitate it around the tank to keep an homogenized mix throughout the tank. And these particular tanks, we like to try to achieve a 1-to-1 diameter to height basis, and we feel we can get a very, very high efficiency of digestion out of these particular tanks based on that mixing and agitation process. Few pictures here of just some assembly, showing a little bit about how the tank is put together. Again, it's spun to a certain level, a short level, very low to the ground, then the beam structures are put on, and then the tank is continually spun up. Internal look at the bag that's under the roof system. And a typical drawing of this particular tank. Majority of this language is both in English and German. But this particular project happened to be in Italy, and just showing a depiction of all the different fittings, the mixing system. We have our mixers that are attached to the sidewall, and we'll show some photos here as we go along of our mixing system as well. The next tank on the list that we have to look at is the universal system, which is simply a flat roof. This is not necessarily a storage vessel for gas. The gas in this case would be pulled off. This also would carry a lot of the same principles as all of our tanks: mixing, heating, and insulation. We have our overflow system and our level control. But in this case, we would simply be capturing the digestate, the substrate, digesting it, and discharging the gas to a separate location. Some of the features of this particular tank is that this tank has a flat roof. It's a stainless steel 316 roof that's pulled across the top of the tank. It's fully supported. It's high snow loads. As you can see in the lower right, it's actually, there's an insulation layer on the top of this particular cover, but this cover is pulled out and stretched in tension across the tank, and then affixed to the outer perimeter and pulled into position. Very unique. The only roof system, I've been in the tank business a long time. I've built lots of covers, lots of domes. This particular roof system is very, very interesting. When I've gotten into the lip system, working with them, it's very, very unique and very interesting across the market. And most all folks that see this get really amazed at how this works. It's a fabulous situation because it allows for the headspace is very aggressive, and this 316 stainless allows for a corrosive-free atmosphere. Again, we have a P&ID similar layout with the first detail that I've shown you. We have the ability to put in a drop tube on the side, mixing on the side walls. Our overflow system is set up such that we drop a shaft on a 45-degree angle, so we're pulling from the center of the tank more or less rather than from the top, and we eliminate pulling some of the foaming and that type of thing from the top. So we simply overflow from more of the center of the tank itself. We can allow for a headspace that does have some ability to collect some gas, but typically these tanks don't create a lot of gas storage. And a little bit more detail of this roof system that I spoke about. As you can look upwards into the tank in this main photograph, you see how the roof system above it is a sealed stainless layer. On the bottom left, it shows how the tank roof is rolled out. It's a thin, very thin, high tensile stainless material that's pulled very tightly across the tank and then affixed, as I said before. In the cases, like most cases, we'll simply roll we roll the roof out, we'll put a layer of insulation and then lay some stone down for a ballast or a support of that roof to keep it, supported and in place. So very unique, very, corrosive-free environment. So it's an excellent process for digestion. The next digester I will show you is our echo system. These are very common looking because obviously the shell is, once you put the cladding on it, would not be depicted as a lip tank. You can't tell it's a lip tank because you've got the sidewall on it, sidewall sheeting. But in this case, simply, these are half sphere DMR covers storing the gas. But as the bottom left shows all the details, we have the gas storage, a dual membrane cover collecting the gas. We have our platforms for access to mixing and some of the nozzles and accessories. And as you see in the bottom right, we have the gas, the blower bag coming down. All of our ecosystems have a blower that runs 24/7, keeping the DMR expanded in place. And again, same situation with these. They carry some of the same features. We have mixing available. We can go upwards of 2.8 to 3 million gallons in volume, which allows us to build fairly large digesters with DMRs. So in this case of more larger applications, these work well. And this echo, meaning this is probably our most economical digester on a cost basis. And typically we can be very competitive in the marketplace with these types of digesters. The P&ID gives you an idea of what this particular digester looks like. Again, we have mixing on the sidewall. And we have our overflow is again the same as I have shown before. Inputs, you have the gas layer at the top, and consequently we can pull the gas off after storage going to the wherever the gas will be transferred to. So gives you an idea how this particular digester is operated. A little bit of detail on setting and pulling the covers up as we build
Hold on
the
one
tanks.
second, Al. We lost
Sure.
audio here. Hold on one second. I think it's on our end. Hold on. Oh, try to unmute, yeah.
Can you hear me?
Oh, yeah, now we can. Yep, you're back.
Ah, okay, good. I'll keep going. I'm running out of time. Want to try to get through all four of these digesters. The Lip Central Unicentral mix system is very unique. And again, as I've used that word many times because these are specialized systems, but this allows for a center stem mixer. We use we partner with a company called Stamo. This happens to be depicting a Stamo center shaft mixing system. This allows the mixer to be supported with a beam roof on the top. And we also have, it's a dual plated roof system. The flat roof is interior, as you can see, for sealing. And then there's a seal shaft, allowable for the shaft to go down through that center and allow the mixer to be placed in, and then also be able to be supported from the roof above. So again, these are, we can get upwards of 2 million gallons with these type of digesters. In this case, it's a 67-foot diameter, 56 high, 50 foot is your fluid level or your liquid height. Again, these are internal plated 316 stainless plated structures for extremely well corrosive free environments for digesters. A little bit more detail, showing a little bit more about how that roof system's put together. And of course, we can build these without the center roof. We've got several of these built here in the States that do not have the center mix system in them. They have maybe a nozzle system or additional mix system in them. But the idea of the high pressure brings these digesters to the table. We're talking about these digesters in a multitude of areas because of the higher pressure operation. So because of the fact that you need a higher pressure, we use a design where we actually pull the internal roof into tension, and which allows the pressure to be achieved. few pictures showing how this mixer is installed. And it's set down through the center. As you can see, again, it's the interior plating of these tanks is all stainless, which is excellent for corrosive-free environment. We have a P&ID showing how the unicentral system is set up with the mixer system coming from the top. Again, we would have a circulating pump system on the sidewall with the center mixing operation, as you see. Just a few pictures of some of our storage tanks that we offer. I'm going to get into some mixing here just in a second. I'm running out of time, but try to get when Tracy, how long do I have here? I'm going through here. Gas collection system.
A minute.
Okay. All right, we have gas collection. I just whip through these slides. A little bit about our foundation, how we lay our heating systems in our foundation, a little bit more of our detail there. I was going to slide down to some mixers real quick. We also have a heating system. It's tubular heating. We wind that around the tank. It's a with a manifold on the outside connecting all the piping, and we run hot water through here, and we heat the sidewall of the tank. So I'm just kind of sliding through here. We set our tanks on foundations that are designed. We design our foundations for our tanks, and we provide all the accessories as they're going up, as you can see. We insulate our tanks and we clad them, typically 6 to 7 inches. We provide exceeding an R value of 20, 25 roughly. Insulation of our mixers. We have our own mixing system that we do provide. We provide a mixer, and one more before I'll get off the line. We provide a mixer that allows you to pull in while liquid in place, so we don't have to empty the tank to service the mixer. So I'm getting through these quick, folks.
Yep,
Just different details, and I think that would be it. I'll finish up. How's that? Got through it in just about in time, but anyway, very fast. But just gives you an idea. We'd love to talk with everybody about our system. We're really excited. We've got a lot of projects we're building at the present time, so we're excited to be in the business. Thank you very much for your time.
Thank you, Al. And if you wouldn't mind just staying on, look at the chat in case someone has any questions. That way you can respond. There's
Sure.
Al's information. And if Eric or Matt want to load up for the next presentation.
Thank you very much, folks. Have a good day.
Thank you. And if you are listed under Scott Furman or name that's not yours, feel free to change it so we know who's here. And if you put yourself on mute, that would be greatly appreciated. All right. Eric, are you good? Are you able to share?
I'm trying right now.
Okay.
Can you hear me?
I can hear you.
All right.
All right. I see Matt as Scott Furman there.
Yep. Oh, I'm Scott. I changed it, I thought.
Yeah, it's still saying you're Scott.
Interesting default. Sorry, I apologize. I thought I fixed that.
You're not the only one. I think we have we're up to 10 Scotts.
I saw your email warning me, and I don't do Zoom a lot, so I'll fix that.
I'm more of a Teams person too.
Yeah. All right, I'll let you go.
Is this coming through okay?
Yep, it looks good.
All right. Well, thank you for allowing us to present today. I guess I'll start off with a little introduction. I'm Eric Haslam. I'm the regional sales manager for the East Coast for a company called Thermal Process Systems. Matt Williams is the West Coast, and he's also the product manager for one of our products called Excalibur, which is an anaerobic digestion technology. I'm actually going to, the title of the slide, I'm actually going to focus on liquid composting, aerobic digestion, which I know you're thinking, well, that's not really what the RFP was about, but it's a unique story that we have for a project in Canandaigua, New York, that is aligned with the landfills and gives you it's a unique disposal option for biosolids that we're a unique company. We fit in certain areas and we don't fit in other areas, and this I think might be one that we fit well and might want to consider. So we also do have anaerobic technologies, and I'll walk through some of that right now. So
Thermal Process Systems, we're a biosolids solutions company that we focus really in that one area. We don't get into the liquid side of the plant. Focusing on biosolids, it's one of the top budget expenses, and it's becoming more so in certain parts of the country, like the Northeast and New England. Our main technologies are digestion related and drying related. So the Thermair in the top left here you see is an aerobic process, which also liquid composting it's called. The Excalibur is an anaerobic digestion technology, which really is our expertise in aerobic technology allows us to manipulate the anaerobic process is really the way I've kind of explained that. The SNDR below is a mesophilic version of the Thermair, if you will. So it's a lower temperature, lower solids destruction process. Biofilter is a technology that we have because our aerobic process, high temperature thermophilic process, produces ammonia. And so we need to make sure that we don't have an odorous facility. So we include the biofilter with that piece of equipment. Then we have solar dryers, and we have a heat assisted solar dryer. So with that, I want to focus on the two-step process that is our mainstay, our Thermair technology. And so the first step is an ATAD, which is an autothermal thermophilic aerobic digester, which I'll talk through in a minute. But basically that first step produces a class A. And then the second step produces a polishing step that eliminates the ammonia and the odors and provides additional VS and TS destruction, volatile solids, total solids. And then I'll talk about the specifics of the City of Canandaigua, New York's project. So where do we fit in the process? You know, you have your wastewater treatment plant that's producing primary and secondary solids. Then they go to some type of thickening typically. In our case, we like to mechanically thicken when possible, the WAS. If in plants, some plants don't have primary, I think this one specifically we're talking about here does, but some of the other ones that are going to be just, providing biosolids to this regional concept would be just WAS, it looks like, waste activated sludge. So we like to thicken to 5 to 7% into our ATAD. And the nice thing about that is that it reduces the tank volume. And then because it's a self-heating process, it reduces the amount of water that we need to heat up. Second tank is the meso air. It's the SNDR is the acronym we'll get into later. And this is really conditioning solids and removing ammonia. And then after those two steps, you see there's on the top left, there's a biogas, off-gas biofilter, and that's just pulling a vacuum through our system so that any leakage is inward, not outward out of the tanks. So there's a vacuum applied to the system. And then it also pulls any remaining ammonia that isn't processed in the SNDR that's scrubbed and clean air is the result, with no odor at the facility. And we give a process guarantee for both the destruction of the biosolids and for the off-gas, no odor. Some places in Canada take this 2 to 3% solids, and we get about 50% destruction, 60% destruction total solids through the process. So a high mass reduction, 50%, 60% reduction. So you have, a lot less material to deal with. And a lot of places like to dewater it, but in Canada, there's a number of places that liquid land apply. And they actually, some places take it directly out of the ATAD, and they don't even worry about the ammonia. They just want the nutrients. Now, land application, we know we're talking about the concerns with PFAS and all that, but and this slide is not really adapted for the specific region of the country and the issues going on in Maine. But instead of land application, we would put landfill cover would be the use. A unique aspect of our technology is that sludge septage fog can be set directly into it. So you wouldn't have to re-wet or, put septage through another treatment process. Only thing septage would need would be, it would need some type of screening for grit rags, those type of things. So autothermal, thermophilic aerobic digestion, the ATAD. Autothermal means no heat is added. It's self-heating. It's a high temperature process. What's nice about that is that it does a very good job of destroying waste activated sludge where mesophilic cultures don't. So we'll get a very good breakdown that you wouldn't get in mesophilic processes. So that's how we achieve the higher total solids destruction. It's an aerobic process and it's digestion, so biodegradation of all the solids. We can't touch the fixed solids, obviously, but we do a very good job with the volatiles. This is just looking into the ATAD with the jet mixing pods. So the thermair is the first step. And the benefits of the process is that the first thing we're doing here is we're getting a very high volatile solids and total solids destruction. And it's making a class A biosolid. So it's a batch process. When you have multiple tanks, you just feed one all day and the other one's isolated cooking all day. So in smaller facilities, it's a little more tricky, but this isn't one of them. So it's not a concern. High temperature, it's a short HRT. You've got 10 to 12 days. So we can get a very high volatile solids destruction, total solids destruction in a very short time. And that reduces the tank sizes tremendously over a lot of other technologies. It's also a very simple process. We do produce ammonia, not methane, but we also then pull that out in the next process tank and eliminate the concerns there. And then we have the biofilter to deal with any fugitive emissions. So the SNDR is the storage, nitrification, denitrification reactor. So primarily it's your campaign dewatering tank that we've turned into a side stream process as well to achieve the following benefits. So it's a mesophilic conditioning step, and the focus is to remove ammonia. So you don't have a large load heading back to the head of the plant. It also makes, if you try to dewater ATAD sludge, it's extremely difficult. And by putting it through this next process, you're consuming additional volatile solids and total solids reduction. It's a short HRT, 6-8 days the minimum. Sometimes a lot of places will actually make it a larger tank, so they just have more storage and they'll actually achieve slightly more on the higher end of the TS and VS destruction range if they go to 12 days. It reduces dewatering cost over just trying to dewater an ATAD sludge, and it creates an odor-free biosolids. And this is the key, is that our material doesn't have an offensive odor. It has it actually smells like, once it's dry, once it's kind of sat and cooled off from 95 after dewatering, it kind of smells like dirt, just like humic substances. It doesn't have an offensive odor. And so that's why the landfills are interested in using it on the landfill as opposed to in the landfill. So that's the big player, is that we're producing a material that landfills want to use to make cover. And it reduces their topsoil costs for their landfills, for their temporary and final cover. An example to walk through kind of just on a 10,000 pound basis. In this facility specifically, it's in, I think, Ohio. We go into the process at 10,000 dry pounds a day, and coming out of that, and we thicken to about just under 7%, which is the max. 7% is about the maximum we would want to go to. So we have 5,000 pounds remaining after that step when you're coming out of the thermair, and that's a 50% total solids destruction. And then there's an additional destruction of, I think it's 15% around, and you get down to about 3,800 pounds. So for every 10 pounds you put in, you get 3.8 pounds out. So you've massively reduced the amount of material you have to deal with. And at this specific facility, they use a centrifuge, and they use coagulant and polymer. Coagulant binds the phosphorus. It also reduces the amount of polymer that we need to dewater. So it's a lot of places. There's a couple places that just use polymer. But it's smaller facilities usually, because coagulant costs $1 a gallon and polymer costs $3 a gallon. So if you can reduce your polymer consumption by half with a chemical that costs a third, it makes sense in a lot of places. So they're getting about 27 to 30% solids. For every 10,000 pounds, they have about 9 cubic yards of material they need to deal with. The summary of this technology is that you get a high volatile solids, total solid destruction to reduce the material you have to handle. We get the WAS is broken down very effectively in the system. So there's less material to manage over other mesophilic processes that are out there. The other thing is the short HRT and SRT allow you to have a very small tank compared to more traditional processes. Now, there are also very complex processes that are out there that use high temperature and high pressure, and they actually get slightly better than we do, but there's a lot more equipment, a lot more complexity, a lot more everything for those. This is a very simple technology, and I'll walk through some of the details of it in a minute here. It's automated, highly automated system, so there's very little operator involvement, if you will. They feed and they transfer and they watch the alarms, and that's pretty much it. Availability. So process equipment. This is a typical breakdown of the schematic. You have a feed into the ATAD. You have a jet motive pump which continually mixes the tank. Splash cones above will knock down foam and help with ammonia stripping and CO2. And then the off gas goes through the headspace to the SNDR and then off to the biofilter. To transfer, we have transfer pumps that go through a heat exchanger to drop it from 140 to 95. And one jet motive pump that continually mixes in is actually is an evaporative cooling mechanism. Simple technology. I want to get to the Canandaigua piece real quick, so we'll just kind of breeze through this. There's very simple equipment. We have pH and ORP for controlling the pumps and the blowers. We obviously monitor the temperature to make sure we meet Class A. We keep track of the liquid level so we don't overfill the tank, the foam level that overrides, and we'll trim the blowers if needed, if the foam rises, and turn up the mixing if needed, and the foam control pump. Flow monitoring, so we keep track of an inventory in the batch process, and there's remote monitoring. We use centrifugal pumps that are very slow speed, hardened steel. We also can use a less energy intensive mixing using a parabolic mixer like the invent mixer. It produces similar mixing dynamics in the tank that we need to effectively get the material to break down. We use PD blowers. The pumps and blowers are VFD controlled. Here's the jet mixing. It's in training air and basically creating very high shear at the nozzle and fine bubble, which allows extremely good oxygen transfer in a thickened tank with a high solids content and a high temperature. And that's part of the magic. And the invent mixer can do the same thing for us, where pumping energy is a concern. There's a biofilter. We won't get into that now, but there's a biofilter. It's a rock media, has a 20-year design life, and the fan's on the clean side of the filter, strobic fan that throws the material, the odors up if there are any remaining up into the atmosphere. So Canandaigua is a small wastewater treatment plant, 6.5 million gallons, but they have a pretty significant solids loading because they've taken a lot of leachate at this plant, and it creates a lot of load and a lot of biosolids. So they originally had 4 anaerobic digester tanks, and they were in need of replacement and doing some type of upgrade, but they also had a lot of nutrient recycle and from the leachate that was coming in, also from the digestion. The landfill disposal rates are increasing in this area significantly because of the pressures from our neighbors in the New England area. A lot of stuff's coming this way and out of the city, downstate, up into central New York. And the amount of biosolids accepted at the landfills were reducing significantly because they're moving towards kind of diversion of organics. And so all these things, they looked at, well, what can we do? Drying and upgrade and anaerobic and dryers. And they said, so this is a picture of the plant. There's the 4 anaerobic digesters. They said, well, let's convert 2 of them to an ATAD and an SNDR. And The benefit of that is that they're going to get Class A biosolids that have no odor. And then the landfill nearby that they take leachate from, they'll use the other available tanks for leachate pretreatment, which will reduce load on the liquid side of the plant. But that's not the focus of this. The focus here is that they want the Class A biosolids for cover, and they're making cover material. They actually were at one point buying farmland and stripping topsoil. They got in trouble for that with the DEC and mining soil. So it was cheaper than buying topsoil, and now they're making their own with poor material from their borrow pit. One of the things also to think about with this is that the nutrient recycle, the phosphorus and ammonia recycle to the head of the plant is very low, which is also of interest to them because they don't want to have more load on their plant. Did I miss something here? Let's see, zero tipping fee at landfill. Yeah, they have a 10-year contract with them because that's the life of the landfill. So some considerations for Portland's problem with respect to this concept is that it's a simple process. I'm kind of thinking of it more of as a two-phase. I think that if we build a relationship with a landfill and talk with them about using the material on the landfill, then there's a pathway that for quite a while could be sustainable. There's an opportunity also to take in leachate, but that's a separate discussion. High tall solids reduction. The other thing is whatever process you're going to put in is going to produce load that's going to go onto the plant. This won't produce significant load because it basically is an inline side stream process as part of our process. I've sent material in the past out to drying companies, Griffin Dryer specifically, when they did a comparison of ours to others. They said it actually dewatered, dried like a Canby material, Canby biosolids in that, because a lot of the WAS was already broken down, that they didn't get this large release of water at a certain temperature where basically the intercellular contents boils and releases all the liquid. So it's going to reduce energy over a mesophilic process, a conventional mesophilic process that doesn't have thermal hydrolysis or something like that. And the other thing is that septage and digested material or undigested material that's coming from another plant can be directly fed into our system without having to be sent through the head of the plant. We have facilities that are as large as the East End wastewater treatment plant. We have an industrial facility that's even larger than these. It's in the 30 to 40,000 dry pound per day range. And so I was looking at the regulations. It seems that with LD 1911, that the prohibitions do not apply to disposal or placement at a solid waste landfill. And we actually are working with Casella in New York and have that agreement in place with them, a 10-year agreement for Canandaigua in place with them. I know they also have a landfill nearby. It's not the one immediately nearby, but it's not too far away. So they may be interested potentially in considering a similar type of thing to what we're doing out here in New York at that facility. And just a picture, we get a very good nitrogen, phosphorus, NPK balance of the material. It's a very nice friable material. You can see it kind of falling out and coming off a belt filter press at 20, I think it's like 25%. And I'll just note that if this stuff is laid down and allowed to just sit for either a freeze thaw cycle or a couple months during the summer, it will dry to around 50 to 60% solids. So that's, you have a place to store it. Most places that are hauling it, instead of hauling it at the 20-25%, they're moving towards kind of laying it down for a little bit and then allowing it to dry so that they can maximize the 40-yard container that they're, instead of filling it halfway and being overweight, they can fill it all the way up and maximize that truck trip. And with that, I kind of breeze through things kind of fast, but we have a short amount of time and I wanted to kind of touch on everything there. And again, one other thing I'll mention is that our Excalibur process is an anaerobic version of this which is very similar. And if there's interest in discussing that and being more in that lane of anaerobic and methane, we would be happy to share more information about that process if time allows in the future.
Thank you, Eric. Does anyone have any questions? Either virtually or in person here? All right, well, we appreciate you taking the time to present. We have your information there, and anyone can always reach out to me if you didn't get it. Appreciate it.
Great, thank you very much.
Thank you.
Yeah, thanks all.
All right, so in 2 minutes, we'll have Veolia. So Frank, I believe you're going to be
Yeah,
presenting.
I'm going to be coordinating. So if you could unshare.
Yeah.
The whole process.
Yeah. Okay.
Yeah, I think everybody can see my screen at this point.
Yes, we can. All
Okay,
right.
can we begin?
Yeah, you're more than welcome to begin.
Okay, so I'm Frank Crean. I'm from Veolia, and we're going to have a team of 3 people that are presented. So I'm turning it over to Jay Sparling, who's the head of our Northeast group. Jay?
Hi, Frank, this is Jay. Can you hear me okay?
Yep.
Oh, great. Okay, I'm just.
So if you want to go ahead and introduce everybody. Yeah, well, Jay's having audio issues. I'll sort of introduce everybody. So on the call is going to be Jay Sparling, who's our Vice President of Municipal Development here in the Northeast region. We also have Christina Gerber, who's part of our technical sales group, and then Tim Muirhead, who's our biosolids expert. So Jay, are you back on? It's not. So what we're gonna do is we're gonna do a quick overview of the company, our approach
Frank,
to
can you hear
delivery.
me?
Yep. Go ahead.
Okay, great. Excellent. Well, thank you so much. You can go ahead and move to the next slide. I apologize for any difficulty with the audio on my end. I just want to acknowledge as we start that this is a long journey for what you're doing, and we really appreciate the opportunity here to share, with Portland Water District what it is that we do, and we hope that we can provide in this process the clarity and the confidence that you're seeking, to move forward with the RFP ultimately. So, Veolia, we are a global business that is focused on water, waste, and energy. And I think when we think about this technical discussion, I wanted to first start with saying that the biggest resource we can bring to bear are people. And we've got a large number of people around the globe that are focused on ecological transformation. And I think that's an important moment just to pause, because you're going to have a lot of wonderful technology selections ahead of you, which are all important. But I think understanding the people that you're working with and making sure that they have the capabilities and shared values are also very important. So you'll see at the bottom of this slide sort of where all of our R&D, our commercial, our engineering delivery capabilities are focused on, which is delivering access to resources, preserving those available resources, and essentially helping the globe replenish them. So that's what we're all about. And as we think about your specific goals, we thought it was important to highlight briefly in New England where we are at commercial scale. I think that's a key theme here is, as you look at the technology, what your core requirements are, who's doing it, how's it going. So in the Northeast, we've had the privilege of earning over 40 years the opportunity to work with more than 50 partners, municipalities. Most of them are asking us to do full turnkey O&M. Some cases we're actually part of the design, the commissioning, but in all cases we're running for multiple decades biosolids treatment facilities. We wanted to highlight two, you may or may not be aware of them. So the two are Cranston, Rhode Island and Naugatuck, Connecticut. Both of these are facilities that the municipalities sized, certainly to take care of their existing needs, but equally importantly, they thought about the regional requirements. But they're doing the regional requirements under a merchant basis and for which we're responsible. What I want to just stand here for a moment, Frank, for a moment. Clearly, there's a technical side and an operations and maintenance side to all of this. But another critical component is how about the community engagement? How about the commercial terms for merchant facilities, particularly consider the regional outreach? How about the partnership as it relates to being aware of and reacting to emerging regulatory compliance challenges? Those experiences are part and parcel to what you hear about from my colleagues, Christine and Tim, in just a moment. Frank, the next slide. So I know that many of us here are familiar with wastewater process treatment train. There may be some that are not. My intent today is not to go through this entire diagram, but it is to emphasize that this is an attempt by us to represent all of the range of resource recovery capabilities that exist, and to emphasize that at every stage in this process, Veolia has deep experience, both in terms of design, so the technical side of it, as well as the operations and maintenance component. So you have over 40 years with Veolia actually running biosolids processing facilities. And I think what's key here is that the ins and outs of actually generating over 170,000 annual tons of Class A biosolids is not an easy task, as you certainly can appreciate. And our goal is to bring, you know, the good, the bad, and the ugly to the story, talk about what works and what doesn't work and how we've evolved in our technical selection and delivery methods. Frank, the next slide, thank you. So in a moment, I'm going to turn it to our technical team. But what I want to emphasize is that when we were considering what Portland Water District's primary goals were, particularly given your aspiration of once you get the green light, 3 years to actually commission, we thought it was important to deliver what we call a one Veolia solution. So certainly Veolia, as you know, do a lot of operations and maintenance. Many cases we're operating and maintaining equipment that we don't manufacture, which is fine. But given your particular requirements, we thought it'd be very helpful, and you'll get a lot more details certainly in the RFI submission, that we talk about for the biosolids processing facility offsite. So we actually are receiving the cake all the way to the point at which we're processing it for final disposal. We wanted to highlight some technology which we think could be very advantageous to you from a perspective of an integrated technical solution. The other thing I want to emphasize, I know there's a lot of necessary discussion here about the technology. The delivery mechanism is also critical. We'll get to this more certainly in our RFI response, but I think it's important to keep in context that at the end of the day, you have to have it turned on and it's got to work. And it's got to not only work, but it's got to be a cost-effective and sustainable. So we think you should strongly consider the progressive design build approach, which gives you, we think, a lot more visibility into the entire process and end up with a better solution. So let's talk about our integrated technology, particularly as it relates to doing it at commercial scale. And I'll turn now to my colleague, Christina. Thank you.
Thanks, Jay. So this part of the presentation, I wanted to just talk about the anaerobic digestion of the biosolids along with biogas utilization. So why do we want to do anaerobic digestion? You know, the biggest advantage to utilizing AD is the creation of this circular economy. You can divert waste organics from a landfill, treat through anaerobic digestion, and transform that into a fertilizer, clean water, and biogas. So we have these 3 streams that can then be returned back to the industrial and residential spaces. You know, and like Jay said, with our passion, you know, being around this reduce, reuse, and recycle concepts, this fits right in. So anaerobic digestion can not only treat just biosolids, but also any food waste. And, you know, this kind of fits into that potential needs of current throughput, as well as any potential additional substrates that you might want to address in the future. And our technologies can treat both. And we have a whole team of anaerobic experts with our experience being extensive, and have learned through these key challenges for each of these projects. We have approximately 12 bio-waste plants, with 4 more in execution. And the first one was commissioned in 2010. And we have over 19 advanced AD installations for biosolids, which includes pretreatment, very similar to this process scheme presented, as well as over 600 other municipal sites utilizing AD equipment. So Frank, could you go to the next one? Thank you. So the first step in this overall process is receiving. You know, we want to include offloading, grinders, organic separation, and grit removal. So some of the key challenges that we've seen is getting the organics out of the AD tanks and the buildup that happens there. So hydrocyclones, shredders, depackaging machines are very imperative to a successful digestion environment. The next step is then a pretreatment, which is typically biological hydrolysis. Class A is not required here, so high temperature for pathogen kill is not required. So a simple biological hydrolysis will suffice. So this step enhances the volatile solids reduction in the digester, which then in turn creates more biogas and renewable energy. So the BH also decreases the anaerobic volume by separating out that hydrolysis and acidification rate of reaction. It separates it from the actual digestion section. So by isolating these biological processes, we actually optimize each of these steps with respect to the hydraulic retention time. And then another added little benefit is better dewatterability for the end solids product. Out of the biological hydrolysis system, the organic waste is then directed to the anaerobic digestion tanks. And this is a mesophilic tank operating at 37 degrees C. But this is the real workhorse of the system. We also have some proprietary mixing in there as well. The organic waste is then converted into biogas, a solids waste stream, and a wastewater stream. So if we follow the biogas train first, the biogas is rich in methane and can be utilized in boilers, CHPs, or upgraded to a natural gas pipeline quality. By utilizing the biogas, the greenhouse gas emissions reduction for your overall facility is appreciable. So it gives the facilities a healthy step towards their sustainability goals. The wastewater stream can then be further processed for reuse or discharge. And all of these discussed processes here are at the core of our Veolia technical toolbox. And because of this, we are able to guarantee performance surrounding the plant throughput, methane yield, and digester performance. If we follow the solids waste stream, that can be further processed with our biocon dryer that Tim will now elaborate on.
Thank you, Christina. So what I'd like to kind of build upon the story of focus around the cake biosolids processing solution and Veolia's consideration of an integrated technology that really at the core, in essence, really achieves the objectives that PWD has defined in its RFI around commercially proven applications at full scale across a wide range of feedstock, fully digested, partially digested, or undigested, which is your as-is material, and that achieves mass reduction and resource recovery and has the potential to decompose PFAS compounds that may be present in the biosolids at high temperature from a thermal approach, and at the end produce an end product, whether it be dried or an inert material that would be suitable for landfill or alternatively beneficial use. So I want to just walk us through an integrated technology approach. Next slide, Frank. That is around indirect heat drying. That is a modular, scalable system that accommodates single or multiple trains for both your current and future loadings, as presented in the RFI for the Deepwater Cake from Westbrook and S and the East End wastewater treatment plants. And as you see on this slide, it's really focused around an integration of two core technologies: our Biocon belt drying system, which we have about 30 plants globally, and there are 10 or 11 in the United States that have been operating for many years, more than a decade, and some as many as 2 decades, on both biosolids that is digested and undigested. And then our energy recovery system that takes the dried biosolids as an energy fuel for heat recovery, and produces a dry inert ash. And this is a water-cooled furnace that can operate at high temperature. The system itself, the equipment, is commercial scaled. It's been operating globally across 3 projects, 2 in Europe and 1 in the United States outside of Minneapolis, since 2008, that can heat biosolids up to the vessel itself rated for 2,800 degrees Fahrenheit. So it has the potential and the opportunity for producing enough time, temperature, and turbulence, what we call the 3 T's, for the decomposition and mineralization of PFAS compounds. So these are the 2 particular unit operations that we have integrated by intellectual property into an integrated solution that we think might be of high interest and alignment with PWD's objectives. On the next slide shows a little bit more of a schematic breakdown of the Biocon belt drying, which is a medium temperature dryer. There are a lot of belt dryers in the industry. This one is proven application, as I mentioned, on all 3 feedstocks of dewatered biosolids, both undigested and partially digested, being a primary material that can strategically and advantageously remove the fiber and the grit content from the material to help in terms of throughput and longevity and capacity of the project. It also of the drying process. We've also have applications for fully digested material, and those that are blended, like primary that's digested and thickened waste activated solids that are not. But it goes through essentially like a pizza oven in through multiple injectors that don't have a single feed point for mitigation of failure of throughput, but multiple feed injectors that go through a drying zone that's at medium temperature, around 350 degrees Fahrenheit, to a lower, warmer end drying zone that's at a lower temperature, but that's a little less than 200 degrees F and lower. And this is all indirect heat, where we're heating the air that's removing the moisture to take it from 25% dry solids as the cake to more than 90% dry as a Class A material, or 95% dry solid as an excellent biofuel for energy recovery, in an indirect belt cabinet that's fully enclosed with a vacuum to remove a small amount of airflow through a condenser for cooling and odor control. But basically, it's a closed loop recirculation air process. The heat medium is using an external fuel, whether it be a hot thermal recovery from our energy recovery system, or another fuel like natural gas to heat thermal oil, that comes in direct contact with, through a heat exchange, the hot air that is introduced into the drying cabinet. So the biosolids are being dried without direct contact of the thermal fluid, which then eliminates the amount of air emission and the treatment requirements, because it's not producing a combustion byproduct like NOx and SOx. So this gives you a little bit of an idea of what the simplicity of stainless steel belt drying, like a pizza oven that goes in the top belt and comes out the bottom 30 or 35 minutes later, as a fully dried material. The next slide basically shows you kind of how we've integrated that very standard application. Like I said, we've got 30 projects, more than 30 trains operating across the globe in the United States around that conventional medium temperature belt drying using thermal oil. And we've connected it to try to really drive an energy autonomous solution, where we're trying to mitigate the amount of external fuel and energy that is needed in the process to really drive a resource of the calorific value of the dried biosolids as a fuel into our energy recovery system. And that flue gas goes through heat exchange. And so there's some off gas that goes through a multi-stage air pollution control system that I'll show in a moment. But much of the heat is returned back to the thermal oil heater that provides the heat medium for the drying process, such that if you're generally around 75 or 76% volatile solids on a nominal basis, you're essentially energy neutral, where there's enough heat recovered from our energy recovery system through heat exchange to fully satisfy the thermal load of the dryer and allow it to be a very life cycle cost-effective process with minimization of the airflow that has to be treated from the process. The next slide basically shows you the schematic of the integration of our technology for round thermal drying to meet mass reduction and create a landfill product, but more so to convert that dry granule into a dry inert ash that is also suitable for landfill and potentially alternative beneficial use. We've used the material to fill the holes of bricks as non-structural fill material, as alternative daily cover, and so it has the potential for beneficial use. But in this scheme, it does show that there is a multi-stage kind of cyclone separation process after the energy recovery that removes the fly ash from the vapor and the bottom ash from the inert water-cooled grate furnace that then goes through a multi-stage treatment before it is atmospherically discharged to meet the most stringent MAC 129, sewage sludge incineration regulations that, quite frankly, is still, applicable to alternative biosolid drying, gasifying processes, even though this is a full combustion that's looking at achieving mass reduction of more than 90%. Drying, you'll get 75 to 80% mass reduction of the as-is cake, and with the added-on treatment of energy recovery, it goes to more than 90% mass reduced from what you started as a wet cake to an inert ash. The beauty of this system, though, is that we are thermally treating with the potential of the decomposition of the and mineralization of the PFAS compounds, a much lower airflow, because we're starting at 94 or 95% dry. So while we're treating the same mass of the pollutants for discharge, the vapor and the airflow is substantially less by maybe a tenth of what you would normally understand and think about in a typical sewage sludge fluidized bed incinerator. So the airflow in this case is something, around 3,000 to 5,000 standard cubic feet per minute to treat 25 dry tons of dried material as an energy fuel. The next slide just gives you a conceptual illustration, if we hovered like a helicopter into the new proposed PWD biosolids processing facility, what it might look like inside the building as a dual train system that has two of the Belcon dryers receiving the cake and processing it into a single energy recovery system that utilizes that heat to heat the thermal oil, and then the off gas of the dryer goes through a condenser and a single stage bio scrubber or odor control scrubber for effective odor control, and the dried material goes into the furnace with its smaller airflow, air pollution control that basically looks like a vent pipe off a fuel oil stove or cooker on the top roof of the building, not a big incinerator stack as you might imagine. And then the dried material is discharged into a hopper or a silo for enclosure of filling of that dump truck before it would go to landfill. So it gives you somewhat a visual look at what that layout might look like for the processing of both future and existing loadings, PWD of your cake. The last slide that we have basically just shows you what the pictures of the Belcon belt dryer looks like on the left-hand side and what the energy recovery system box looks like on the right-hand side. The furnace itself fits within a building. That's actually the picture of the facility in one of our operating plants that's really very compact and very effective for creating a sustainable and energy autonomous biosolids management process over a wide range of feedstocks, both digested and undigested material.
Yeah, I want to thank everybody for the time, and we have just, I'm not sure how close we are to the end here, but maybe if anybody has any questions, you can reach out to me. My name is Frank Crean at veolia.com. That's my email address, and I can get you answers. And with that, go ahead.
I was gonna say, we don't see your email address on here, but we did have one question in the chat: is what size footprint with the Biocon ERS system take?
And that's a Tim Muirhead question. Go ahead, Tim.
Yeah, basically, information will be illuminated with a drawing and some more dimensional details in our written response to your RFI. What I would say just generally as a kind of point of reference, each of those Biocon belt dryer with the size that can handle the future and existing loading is about 25 feet wide, about 55 feet long, and about 30 feet tall. So that's kind of a unit size per dryer that would sit either head to toe or side to side. And then the energy recovery system is added on as a modular system that can be installed right up front at the same time or installed in the footprint of the building, but we'll enumerate and kind of detail that out in our written response.
Okay, thank you. Yeah, I
You're
think that was
welcome.
just more of a general question.
Okay, like I put my email in the chat. And,
Perfect. I see that in there. We have 2 minutes. If there's any questions, if you're online, just unmute yourself and ask or type it in the chat. Anyone here, just take yourself off of mute and ask the question, please. All right, not hearing anything. Thank you, Veolia team. We appreciate you coming in and presenting on your different technologies. We are now at break. So this is lunch on your own. It's for 90 minutes, so we'll come back at 1. I actually got the time right this time. And we'll see everybody back at that time. So go do what you have. So give me a minute and we'll start. And anyone here, yeah, if you just put the button here, put your mic on, and I push the hot button that you put on mute. All right, we're gonna get going in a minute. For those online, if your name is Scott Furman and you are not Scott Furman, feel free to go in and rechange your name so that is your actual name.
You Scott Furman if they like?
You can. All right. Why is it this one? Oh, here we go. There. Okay, so can you move it? All right, we are at time. So Chip, if you want to start us off with our first dryer talk of the day. And if everyone online can mute themselves, I would appreciate it.
All right. Hello, everyone. My name's Chip Plus. I work with LCI Corporation. I want to thank, Tracy and her team and Scott and his team for allowing us the opportunity to come up here and present. I'm going to present today on the thin film dryer. Some of you may be familiar with it, but I assume most of you probably aren't. It's not a very common technology. The first thing I wanted to go through was just kind of the state of where we are up here. I'm not going to go into large detail because everybody knows what's going on, but I know right now there's short-term actions that are happening, and then I think the longer term, we don't know exactly where we're going to go, whether it's thermal destruction technologies, source reduction of PFAS, what's going to happen with the state of biosolids. So I think in the future, I think everybody needs to look at the technologies, the processes to be flexible in the future and be able to adapt to whatever process you may need in the future. So the thin film dryer itself, the best way to show it is, let's play this animation. There we go, is to play through an animation. So I'm going to show you an animation of the unit. The full animation's on our website. This is kind of halfway through. This is a shorter presentation, so I wanted to get some points across. This is the system all the way through from the feed system, through the discharge system and the condenser system. If you take a look at the unit, we use either steam or thermal oil, and we put that in the jacket around our dryer. That's our heating medium. It heats up the dryer, and then our rotor and blades, they start spinning. And then we start the feed pump. The feed pump pumps sludge directly into the dryer, and those blades and rotor will spread and convey the sludge through the dryer. So this is a cross-sectional view of the dryer. The heating medium's on the outside circumference, and these little blades, they act, I say act like putty knives, where they're painting the sludge in a thin film. That's where the term comes from. They paint it on a thin film, and then the heated surface heats up the sludge and boils the water off into those little channels where it's pulled out of the dryer by a fan. So the sludge always comes in a sludge phase and goes through a sticky phase. So every time you're going to go through a sticky phase, which is a very difficult phase to handle, and then you'll go out in a granular phase. The material is going to come out at upwards of 230 degrees Fahrenheit, so it's going to be very hot. So we use a water jacket cooling conveyor to cool the sludge down to about 120 degrees Fahrenheit. And then it discharges through a rotary valve. The purpose of the rotary valve is we limit the air intrusion back into the dryer for safety reasons. So the sludge is going to go right to left. The vapor is going to flow left to right, and it goes out to a simple mixing or barometric condenser where you'll spray plant effluent. It cools down the vapor stream. 95% of the water will head back to the wastewater treatment plant in the form of condensate, and only about 5% is going to exhaust out in the form of moisture. Went too far. So I wanted to put this together because there's a couple pieces of equipment that aren't here. The first part is a steam or thermal oil heater, which is on the upper left. It doesn't actually have to be a heater. It can be some sort of heat exchanger where you're pulling heat into steam or thermal oil to be applied to the dryer. The bottom right, I show a silo for sludge storage. Doesn't have to be a silo. It's just a placeholder. And over on the upper right, I show a thermal oxidizer, specifically because here in Maine, that's what we're talking about as far as destroying the PFAS. Typically, you only need to use something like a biological or a chemical scrubber, but from what I'm hearing for PFAS going out in the air, we may need a thermal oxidizer. And so I put the PFAS in red just to show where it's going to be discharged. We all know it's going to go out in the sludge. Some of it will probably come back in the condensate to the plant. Those two streams will be contained, right? The big issue is that stream that's going to go out with the exhaust flow that we all have to consider. So I think that's one thing that I wanted to point out to you guys when you're looking, especially at dryer systems, is the emissions control system may need to be some sort of thermal oxidizer in order to control that PFAS. So as far as our dryer, am I back on? All right. So we've had installation since 1985. So it's a proven dryer in many applications, and we've had a wide variety of applications. The same dryer can actually dry to different dryness levels, which is another point I have here. We can take a wide range of feed sludges into the dryer. We have a very small exhaust airflow, low energy usage.
Yeah, I think they're all. Oh, is yours on still?
I popped it back. Am I back? There we go.
And then charge them up.
And then, so we can recover heat for other processes. I'll get into that in a little bit. And then also as far as a regional dryer, the fact that we can accept a bunch of different sludges makes it well suited for regional drying. So about as far as flexible applications, the big deal is we've dried sludge anywhere from as low as 30% DS coming out all the way up to 95% DS. Same dryer can do these with some slight modifications. So let's say today you want to go and landfill at 60 or 75% sludge, and you want to go to 95 in the future. We can take that same dryer and reconfigure it to do that. Or, in Europe, we use these a lot for fluidized bed incineration, where we'll be drying to plus or minus 40% solids. So that same dryer can do that as well. As I stated, we have, we started our first installation was in 1985. Since then, we have 119 installed globally. 40 of those have industrial contribution or fully industrial installations. We've taken sludge in anywhere from 10% solids all the way up to 55%. And then I mentioned we can discharge over that 30 to 95%. And then at the bottom, we've had a lot of mono sludge incinerators, incineration applications, which basically means sewage sludge only. We've done co-incineration, which is a mixture of incineration sludges, or a mixture of sludges in the same, a mixture of sludge and other waste in the same incinerator. And then agricultural use in landfill. We have quite a few installations on those as well. Oops, went the wrong way. So I wanted to talk a little bit about the exhaust airflow. We can exhaust with our smaller dryers down to about 10 CFM. Our largest ones will only output about 200 CFM. And this is very important, again, as we look at the flows coming out for PFAS. So a lot of times what we do is we redirect the airflow back to the thermal oil or steam boiler system, and it can be burned with the combustion air, or it can be sent to the incinerator, or maybe in this case, the oxidizer for the syngas, and it can be burned up with the thermal destruction technologies in that way to destroy the PFAS. We have a very simple system, a very small airflow fan. The other thing I want to mention is we don't use packed media in our condenser. Packed media has a tendency to foul. I've seen FOG, I've seen sulfur, even hard water from the cooling water that will foul on these little balls you can see over to the right-hand side. And they become very difficult to clean. Our open condenser system has no risk of fouling. There's no media inside there to foul. So I want to go through our design and maintenance a little bit. We don't have a back mixing system, extruding system. We have no feed system. I call it a pump and a pipe. We have a progressive cavity pump that pumps directly into this feed nozzle you can see in the middle. And that's where the rotor and blades take over and spread and convey the sludge through the dryer. So therefore, outside of the pump, there's zero maintenance on our feed system to our dryer. We also have a single fixed rotor. The rotor is not heated, so there's no rotational items that we're having to put that have joints for the thermal fluid to go in that would risk leaking. And then we don't have any tensioning or alignment. It's aligned on two bearings. Once it's on those bearings and it's set, it's ready to go. It's also self-cleaning, so it will clean itself out, and it cleans itself out in about 15 minutes. So I'll talk about it now, but I'll talk about it a little bit later. If you're going to run limited hours like 8, 12, 16 hours a day, this dryer can shut itself down very quickly and will shut itself down without any sludge inside the dryer. And then maintenance. We have this pre-configured trolley system that comes with each one of our dryers. You can see on the bottom right is our animation. Then our wear part is the blade that you see on the lower left of your screen. It's simply bolted to the rotor. The rotor's designed for the life of the equipment. And each one of these blades are not replaced every time. The last time we did maintenance on our units in New Jersey, one of the units had no blades that needed to be replaced. The other one had, I think, 10 out of a couple hundred blades that were on that dryer. The other thing is it's basically bolting. You unbolt and disconnect the motor side flange. You bolt up a trolley on the opposite end. And there's no heavy lifting, and everything stays connected. Even the motor gearbox, you just disconnect the electrical, but you leave the thermal fluid connected, you leave the vapor line connected, you leave the feed line connected, and the discharge line connected. So it makes the maintenance as simple as possible. So these are some pictures. We have an installation in Middlesex County, New Jersey. That is the picture on the upper left. They pulled the rotor inside a building. They had an existing building with plenty of room. So they pull the rotors there and do their maintenance inside the building. On the upper right, that's another installation of ours where they do maintenance outside. So typically, the motor is put right at a roll-up door, and you would roll that rotor out on railroad tracks, I call it, and you would do the maintenance outside. That way, if you're putting a new building in or you have an existing building, it doesn't take up a large footprint for you to have to do maintenance. Maintenance is typically once every 8,000 hours or yearly. It really depends on really how trashy your sludge ends up being. Middlesex does theirs on a yearly basis. They put about 6,000 hours on their dryers a year. And as I said, again, they had one dryer that didn't need any blades replaced and one that needed about 10 replaced. In the bottom in the center, you see the opposite end trolley. We put this trolley on the shaft on the non-driven end, and it rides on the heating jacket through the dryer, and that's what supports the opposite end during maintenance. So we'll talk a little bit about the configuration. We have dryers that go down to as little as 100 pounds an hour of evaporation, up to 15,000 pounds an hour of evaporation. So we have a wide range, and we're also well suited for smaller plants. I know some smaller plants out there are starting to look at drying. And typically that hasn't been the case with most dryers. Most dryers are designed for larger plants, but we were able to do very small dryers. We can do the continuous operation. Most dryers do a 24/7 operation. But as I mentioned, we can very easily do an 8-hour, 12-hour shift. It takes about 60 minutes to start up the unit. And that's typically the heating system that needs to be started up. And then it can empty itself in about 15 minutes and do a complete shutdown in about 30 minutes. We have sludges that are undigested, and we have digested sludges and industrial sludges. So we're very flexible on the type of sludges that we can take in. And then I've already mentioned our ability to vary the discharge percent solids depending on the application. And finally, we do have a high turn down capacity. We can run the dryer at about half of its rated capacity by varying the drying temperatures or turning off some of our heating sections. I always like to talk about safety. It's very important in a dryer. As I don't know if you guys know, but there have been fire and explosions related to drying systems. The main way we keep the dryer safe is we take oxygen out of the equation by using an inert atmosphere inside the dryer. So we limit the air intrusion inside the dryer, and we limit the oxygen to less than 8%. We measure the oxygen level, and if it goes above 8%, we either inject water or nitrogen to maintain that inert atmosphere. We also have gaps. There's nothing inside the dryer to cause sparks. There's gaps between all of the components. We're also an indirect heat source, so we're not putting any burnt or spent fuel or combusted gases into the dryer. And then finally, we're fully enclosed with negative pressure, so we're pulling air into the dryer, and we're not pushing anything out into the operational room. And we maintain this inert atmosphere during startup shutdown through faulted conditions. So I wanted to talk about undigested sludges for a while. They are a little more challenging than digested sludges to dry for a number of reasons. The first thing that we've known with our experience over the years is they're hard to dry. So normally the dryer needs to be derated, and you need a larger dryer in order to evaporate the same amount of water. They're also, as anybody can know if you've been around, especially undigested primary, it's a very odorous application. I joked with operators all the time. I'm like, if your cake smells really bad, it's going to smell really bad when it comes out of the dryer. So that's another thing to take into consideration. And with the thin film dryer, we lower that exhaust flow, which means your odor control system or emission control system can be smaller. Also, if it's not digested, I typically have seen fats, oils, and greases come into the condenser system. And the condenser acts like a big thermal heat trap at that point, and you can get big chunks of fog in your condenser system that has to be cleaned. Middlesex County has an undigested sludge. They have this open barometric condenser. They've never had any issues with fouling inside the condenser system. Next, it's more combustible. Since it's not digested, it has more energy potential. So the dust or the dry sludge is more highly combustible. So that's another thing that you need to take into consideration. It's very important to empty the dryer. I feel like when you have an undigested sludge, or at least to make sure the sludge is fully dried. Leaving partially dried, undigested sludge inside a dryer, it comes with some risks. And then finally, as there's more fiber in the sludge, it's typically lower in density. So it can feel like almost like cotton candy, depending on the type of dryer you use. It can be very, very light. So those are some things to think about if you're looking at drying undigested sludges. It's not that it can't be done. It's just a little bit more difficult, and there's some things you need to think through. So we'll talk a little bit about thermal energy consumption. I've seen published values anywhere from 1,150 up to about 1,600 BTUs per pound of water, depending on the dryer that you're using. Many dryers recover heat, but they use that for the drying process itself, especially direct dryers that use heated air. They recover their heat from their exhaust air and pull that back to preheat the incoming air. Indirect dryers typically don't do that. Our dryer is an indirect dryer. Therefore, we can recover the heat and we can use that for other processes. So we typically use 1,150 to 1,300 BTUs per pound of water. So we're on the lower end. It varies depending on how dry you want to get the sludge. There's some physics behind that. If you have any questions, I'll let you know. It's not that you're using more energy. It's just you're using more energy per pound of water that you're evaporating. And we can recover the heat. I think I already mentioned that for other processes. I wanted to mention partial drying as far as heat consumption. You can use 10 to 25% less energy just by dropping the dry solids that you go to. So if you don't need 90%, you can back off to 75 or even lower. You can decrease the amount of heat that you can use or you need to use. So let's talk about heat recovery. So heat flows from high temperature to low temperature. So we put into the thin film dryer a thermal oil steam somewhere between 350 and 400 degrees Fahrenheit. That'll heat the sludge and vaporize the water, which goes to the condenser, and the vapor, therefore, since it's evaporated, it'll be at least at 212 degrees. So in the condenser system, we can pull that heat back out and we can recover up to about 85% of the heat put into the dryer in the form of hot water at up to about 185 degrees Fahrenheit. So where's that useful? So we've used it for digester heating. I've seen it used for building heat. Tracy and I were joking at lunch about district heating. I've seen it used for district hot water, industrial processes, or we've preheated the sludge prior to dewatering. So I'll talk through a couple of installations to finish this up here. The first one I want to mention, I've already talked about it a little bit, is Middlesex County, New Jersey. They have 5 of our thin film dryers that have been operating since 2008. We are drying an undigested primary secondary sludge. And the specification was we had to dry from 27% to 51%, which is what I put on here. And we were going to evaporate about 8,500 pounds of water. They actually can only dewater to about 20 or 21%. And they found for their process, which is a lime stabilization process, they needed about 55% out. So we ended up outperforming what they asked us to do with our dryers there. Instead of drying 27 to 51, we're drying about 21 to about 55%. I mentioned Integral Turkey. This is used for incineration. It's a mono incineration plant. The main thing I wanted to point out here is they recover heat off the incinerator and they heat thermal oil with the heat exchanger system up to about 445 degrees Fahrenheit, and that's what heats the dryer. And then they recover the heat off of the condenser system and they heat the sludge up to about 100, I think it's about 100, I think that's wrong. It's about 100 degrees Fahrenheit before it goes to the centrifuge for dewatering. And what they found when they heated the sludge, I just mentioned this quickly, is it improved dewaterability about 2 to 3%. And that ended up reducing the amount of energy they had to use in the dryer. This one I want to mention, this is a typical application in Germany now for fluidized bed incineration. We're drying to about 38% here in Karlsruhe, Germany. These dryers are evaporating about 6,200 pounds an hour of water. In Gifhorn, Germany, I wanted to mention this because this is a very, very small dryer. They're only evaporating about 800 pounds an hour of water. So I wanted to point out that we have a wide range of dryers, a wide range of sizes that we can offer. And then finally, one of our industrial applications that's been running since 1996 is on basically a fiber sludge, a biological fiber sludge. This is operating at about 4,400 pounds an hour of water, and they're drying up to about 90% solids. So with that, I think that's all that I had. My contact information is there if you have any questions.
Great, thanks, Chip. Anyone here in person have a question? I'll pass you the mic or bring it over. The working mic. All the batteries apparently died. If there's anyone online who has a question, feel free to unmute yourself. All right, well, thank you so much, Chip, for making the trip up here to present about the thin film dryers. And all right, so I'm going to stop sharing here. All right, so then next up, we're going to have in 2 minutes is Andretz. Stephen, are you on?
Yes, I am.
Okay, if you want to pull up your presentation and give us a minute to try and transition.
Thursday, we should charge the mic during lunch.
Yeah. Bring your own bag. All right, yeah, there it is. Oops. Okay, if you want to go ahead and start, feel free.
Okay, you're able to see the presentation?
Yep, you're good.
Kind of running blind here. Okay. So my name's Steve Haggerty. I'm with Andretz Separation. I've been in the business since 1989. Started my career on the dewatering side of the business with the Bird Machine Company. And Andretz acquired us in 2003. And I've been in the dryer side of the business on the service side and now in capital sales for about the last 10 years. So Andretz is a leader in drying systems. I can't control my, there we go. We've been providing thermal systems since 1972 in the municipal industry, a little bit longer in on the chemical side of the business. We have basically 4 technologies that are appropriate for the municipal market: the fluid bed dryer, a paddle dryer, a belt dryer, and a drum dryer. And I'm going to talk briefly about each one of these to try to fit it all in. And of course, we know that drying results in a huge volume reduction of solids. From liquid sludge, it's about 30 to 1, about 8 to 1 if you're dewatering sludge and disposing of it. Andretz prides itself in building plants to cater to the fertilizer industry, making agricultural grade products with our dryers. Our drum dryer produces the best quality pellets or prills for inputting into ag spreaders, and they're pretty reliable. As a result, it also makes a very good product to feed to a cement plant, or in the case of these pyrolysis technologies, uniform or scientific feed to benefit pyrolysis systems and gasifiers. So this is just a typical example of the products that come out of our dryers. The This belt dryer is actually a competitor's product. It's not back mixed, and it's just simply dropped on the belt. It results in a very low density, lightweight, friable product. But the belt dryer, the drum dryer, the fluid bed dryer all make a very uniform product, and the paddle dryer makes a more amorphous, broader distribution product. And as I said, it can be used in cement plants. It can be used as enhancement to incinerators. It's got the BTU value of a low-grade coal, and yeah, I'll talk about that a little bit later. And there's basically two ways of drying that you've probably heard already. There's direct drying and there's indirect drying. Indirect drying uses heat exchangers to transfer the heat to the sludge and evaporate the water vapor. And direct drying is directly introducing the sludge into an airstream of the process that's been heated directly with a furnace. We've built our dryers in just about every kind of configuration, whether a new building or site limited in an existing facility. This is a picture of Pinellas County. The dryer building is here. You can see the heavy residential area around this facility. So it's very sensitive to odors, and we use various odor control systems to enhance the operation and keep odors down. And then, one of the big considerations anybody has to consider is what the fuel source is going to be. We've built dryer systems on natural gas, on dual fuels, on actually triple fuels. And in the case of Philadelphia, that plant can run on fuel oil, natural gas, digester gas. We have a plant in Manatee County that runs completely on landfill gas. The landfill gas is sent to the dryer uncleaned, and we burn it directly in our furnace and heat the drum dryer with that. We've used waste heat from generators. We can use industry heat, boilers, steam, the waste heat from pyrolysis. The pyrolysis exhaust can be directed directly into the plenum of our dryer, and the syngas can in turn be burned in the furnace and mixed with that exhaust gas to create significant reductions in fuel demand. If there's a digester involved, sometimes these processes can be energy neutral. One of the things that our experience brings to the table is that we're able to effectively size our facilities in conjunction with the customer's process, and we can guarantee the results, both the evaporation rates and typically the particle size distribution as required. So our flagship technology is our drum dryer. We have over 40 drum dryer lines in the United States. We have 2 under construction right now. We have a big plant in Philadelphia, Pennsylvania, and a newly commissioned plant in Dallas, Fort Worth. The drum dryer essentially has a process hot air loop that continuously circulates gases in the dryer system. We feed the dryer with recycled material from the solids handling process, and we mix that with wet material from the dewatering system. We mix that in a plowshare mixer, and we introduce it into the hot air stream. It discharges the dryer. The solids are separated. The dust continues to a dust separator, and the hot vapor reports to a simple tray condenser where the water vapor is condensed. The hot air returns back to the furnace and is mixed with the combustion gases in the furnace. A slipstream is sent off to the odor control unit. Product is sized here. The rejects report to a crusher. All the rejects end up in the recycle bin and mixed with the wet incoming feed. And we typically cool the product before discharging it to a storage unit, which could be a shed or a silo or whatever the customer desires. This is just a cross section of our triple pass drum dryer. The hot air and granules come into the center of the drum where it's mechanically lifted and entrained into the airstream. And as the moisture is released, the density drops in the particles and it becomes entrained in the air flow and out the exhaust duct. This is our latest facility, which was just recently commissioned in Dallas-Fort Worth, Texas. This dryer system has a capacity of evaporating 14 tons an hour. And it's a very complex system where we recycle all the water and do some heat recovery as well. There's a lot of trash in this particular facility. We don't know if that's going to be a continuing problem or if it's just issues with startup. So we supplied the drying system and 4 dewatering centrifuges to this design, build, operate system operated by Synagro. And then, as I stated earlier, we can use multiple types of gas: natural gas, digester gas, landfill gas, and syngas from pyrolysis or gasifier processes. We also have an Andritz belt drying system, which is very popular worldwide because we can use waste heat from different processes through the use of heat exchangers to heat the air in the plenum, which travels through a uniform layer of solids that are formed on the belt by the feed system. And by creating a uniform layer of solids here, all of the hot air has to pass through the layer of pellets in order to exhaust the dryer system. It's very slow moving, not unlike the materials that you see on belt presses, a little bit different fabrics, but the same general concept. And again, we have a process air loop. We can direct fire. We can use heat exchangers from steam or solar heat or waste heat from other processes or heat from a gasifier. And again, the feed is introduced via a back mix system, which we hold a patent on for belt dryers. And by doing so, we're able to formulate a granule, the discrete particles on the belt, and dry them uniformly and have some control over the dryness and the product output. And all of these dryers are controlled by the outlet temperature. Again, the water vapor reports to a condenser. A slipstream is removed from this for odor control, and the product reports to product storage via some type of cooling device. In this case, this is a belt cooler. The benefits here are we can handle digested sludge, undigested sludge, mixtures thereof. We have flexibility with our feed system, and we back mix so that we can formulate a uniform granule. We also manufacture a paddle dryer. This is a direct contact dryer, and it's a much simpler flow scheme. We also feed wet cake into the dryer where it contacts these paddles, which are have thermal oil inside them, and also the jacket of the body of the machine is also heated with thermal oil. And after a certain retention time, we're able to discharge granulate into a cooling screw, and then, well, there's supposed to be a screen under there. Again, the slipstream that reports to a scrubber, and the exhaust from the scrubber goes to odor control. Benefit of the paddle dryer is it's got a very low airflow requirement. So it's a model of our paddle dryer. We protect the paddles with a tungsten carbide HVOF coating. It's held up very well so far. It's not widely tested. We've got a plant on undigested sludge and digested sludge that has held up quite well. This is the typical body of the dryer when it's filled with sludge. So the wet sludge comes in at the feed end, and as it transitions through the plastic phase, it becomes more granulated just prior to discharge. This is a fluid bed dryer in Zion, Illinois. The fluid bed dryer is also an indirect dryer where we can pass steam or thermal oil through a heat exchanger, and then we force air through the heat exchanger and through the granulate that's inside the dryer. Much like a hot air popcorn popper, this becomes fluidized, and as the granulate dries, it moves along the dryer from the feed zone to the discharge zone and discharges dry granulate. The air, again, we have a process air loop. The air comes into the dryer through the heat exchanger. The process air leaves with dust and water vapor to a cyclone. The dust is separated in the cyclone. The water reports to a condenser, and we return that hot air back to the dryer, on and on. The granulate leaves the fluid bed dryer, reports to a cooler. The discharge from the cooler reports to product storage. And again, we can back mix, or we can mix directly into the fluid bed with our feed system. Typically have low emissions because, again, this is a gas tight operation with in an inert environment, and it has a very low off gas discharge. All of our dryers are NFPA compliant with dust and fire hazard mitigation. We use chemical suppression and flameless venting to ensure worker safety and to protect the owner's investment. Typical odor control strategies that we've employed successfully are chemical scrubbers, are thermal oxidizers, and biofilters. Some recent successes, we have a design, build, operate system for Synagro in that CRD in Victoria, British Columbia. This is a new plant that's not located at the site of a wastewater treatment plant. It's 18 kilometers away at a landfill. We have a sludge receiving tank that we receive the sludge with a pipeline. It goes into a digester. The digestate's dewatered and fed to the fluid bed dryer. The gas operates the dryer. There's no outside fuel used at all to operate this system. The dried granulates, the plan is to ship them to a cement plant in Vancouver. I'm not sure that that's taken place yet, but they're contractually obligated to do that at some point. Some other recent improvements, we've added some automation to our belt press dewatering equipment at Ocean County, New Jersey. The result is that we reduced polymer consumption by about 18% through advanced automation and in our control systems. Andritz is one of the largest systems integrators in the world, and we're always advancing the automation of our plants. We've also recently done some experimentation with THP sludges, and we've come up with some strategies to create effective granules to stabilize the THP sludges so that they can be used and stored safely and transported in a dust-free manner. We've also used fluid bed in conjunction with circulating fluid bed gasifiers. This is important as opportunities come up to use pyrolysis or gasifiers to destroy the PFAS chemicals that are existing in these sludges, and to be able to recoup the heat from the pyrolysis system and to take advantage of the syngas produced. We can, with a drum dryer, we can probably reduce the energy consumption by about 35 to 40%. And we service all the equipment that we sell. It's a big part of our business is the ongoing support of our customers. And part of that support is the ability to transfer knowledge that we learn from our customers to our other customers. And that's all I've got.
Awesome. Right. Thank you, Stephen. All right, we have an echo. Is there anyone that has a question about the Andritz dryers? Anything online? Okay, so we have about 5 minutes till our next presentation. If Huber, I don't know who's on. If you want to go ahead and Dieter, thank you. If you want to go ahead and tee up, give it a few minutes, and then we will start.
Hope you can see my screen.
Yes.
Okay, so
Yeah. It's in the non-presentation mode.
I'm just trying to. It should switch now to the presentation mode.
Yes, it's in the presentation mode.
Okay, so we wait just another 4 minutes.
I would just do a minute, let people settle here, and then we'll just go ahead and start. Let me switch this so you can see.
This is a good opportunity for all the Scott Furmans out there to identify themselves. If they dare.
Yeah, we want to know who the Scott Furmans are in the world.
Andre Brusso.
Hey, Andre, you gotta change the actual name.
I want to be Scott today.
Everyone wants to be Scott.
It was fun at first, now it's a little unsettling.
Well, Scott, I was on a call with your boss earlier today, and he was impressed that there was 8 Scott Furman. So I don't know, maybe your paycheck will increase.
Yeah, Seth did mention that y'all were on a call even earlier. And you guys were Scott Furman. All right, if you do want to go ahead and start, and we'll just give you the 25 minutes from now, and we'll just
Okay.
take a longer break.
Perfect. So I'm going to talk about the Huber belt dryer. My name is Dieter Weinert. I'm the product manager for our thermal drying processes, what we have. I will briefly talk about the company Huber Technology, point out the key features of our Huber belt dryer, and then finish up with some installation examples and our US installations, what we have right now. So Huber Technology is in the business now for more than 150 years. We just had the 150 anniversary last year. It's owned by the company, by the family Huber, and it's still a family-owned business. So the current owners are Georg Huber and Johanna Rong. So here's just a timeline of the tradition and then quality and innovation of the Huber Technology company. So since the late 60s, so we are active in the area of wastewater treatment and also biosolids handling. So overall, Huber is active worldwide. In the US, so we are one of the many subsidiaries Huber has worldwide. We are currently here in the US employing about 120 plus people of the overall almost 1,500 people worldwide associated with the Huber Technology group. Meanwhile, so our office here in Denver, North Carolina is the second largest production site for Huber equipment worldwide. We are currently in process of about 140,000 square feet addition to the existing plant, which will be operational early next year and will allow us really to manufacture all Huber or almost all Huber equipment here in the US, including the belt dryers. Overall, we are active in different areas of the wastewater treatment process. It starts with safe access solutions like doors, pressurized doors, and then covers. But our main focus is really on wastewater treatment, mechanical treatment, stormwater treatment, and then biosolids handling, whether that's thickening, dewatering, screening, or thermal drying. So that brings me to the key features of our belt drying system or our belt dryer. Overall, you have heard it already a couple of times now. I mean, it's nothing different. We start always with a cake hopper, so we need the dewatered cake. It is transferred with a cake pump to our belt drying system, which is the center of the processing facility. The belt dryer receives thermal heat, which is indirectly transferred to the air moving through the dryer and removing the moisture from the dewatered cake, which is placed on the belt. Actually, our belt dryer is consisting of two belts. We have an upper belt and a lower belt, and both belts are transferring the sludge from through the entire dryer system. So it makes one way through the whole belt dryer on the upper belt, then it drops down, and then it makes it way back through the dryer system to the discharge point. Dried material then is conveyed into a storage facility. It could be just a dumpster or a truck loading system, or for larger facilities, we normally do also silos, which then normally come also with nitrogen system and dust collection. The airflow through the dryer, so we have two options available. We have a one-pass system, what we call fresh air system. So we just take the air preheated, and then it goes through the dryer, and then it's directly discharged. Or we do a condensing system, so that means we are extracting the evaporated water and using, which gives us the opportunity to reuse the condensation heat and the air coming out of the condensing system is then preheated again and returned back to the belt drying system. Just a couple of pictures and impressions of the different items needed for the overall drying process. Like I mentioned, the first step is always a cake hopper. It depends on the throughput and the operation hours of the dewatering system. If the dryer more or less runs parallel to the dewatering system, it could be a relatively small hopper, like you see here on the left, right lower corner, which is probably just a 5 cubic yard hopper with a directly mounted cake pump to it. Or if the operation hours of the dewatering system are significantly different to the dewatering to the dryer operation, so we can also provide larger cake hoppers, like 35. The largest one we have done is almost 280 cubic yards, and that's always more or less project specific designed, depending on operation hours and operation schedules. I said the cake is always transferred with a pump, with a progressive cavity pump to the dryer, and placed on the belt with this extruder device, which creates this noodle type layer or spaghetti, which is more or less the key of the dewatering process, because it provides a high porous layer where the air can easily go through the layer and heat up the sludge and remove the moisture. So this extruder is so really key to the dewatering, to the drying process, generating a homogeneous sludge layer, which allows a constant and an even flow of air through the sludge layer as the material moves through the dryer. Just wanted to start a short video, which which just shows a little bit the operation. If I can get it started. So the pump is transferring the sludge to the extruder device. The extruder head is just moving across the entire width of the dryer. And as the head is moving and the pump is pushing the sludge through the extruder head, it places these strings of material of dewatered cake on the belt. When it reaches the opposite end, the belt indexes and makes space for the next layer, and then the whole extruder head just moves back to the more or less to the home position. And this process is just continuously going forward and placing sludge on the belt and moving it into the dryer box. we have multiple different sizes of dryers, but they are all consisting of this, more or less the same type of module. So we start with a 2-module system, the so-called BT4, which consists of 2 of these modules. What you can see here is with a fan on top of it, which moves the air through the system. And we can go up to a BT30, which means we have 15 of these modules side by side. So it's a modular system. So we have one design and we can just easily add additional modules depending on the desired throughput of the system. So the overall design, like I said, with the different modules and the process air fans on top of it, they are moving the air through the dryer. So the sludge layer is placed on the belt at the headpiece 1 with the extruder, here shown on the left. And then on the upper belt, the material makes its first way through the entire length of the dryer until it reaches headpiece 2, where it drops down to the lower belt. And then the material is transferred back through the entire dryer length, back to headpiece 1, underneath the extruder system where the discharge takes place into the conveying system. The design of these systems is always that we want to achieve class A. So that means at least dry to 90% plus dry solids content, so less than 10% moisture. Key part of the dryer boxes are the rows of heat exchangers, like indicated here. There's one row underneath the upper belt and another row of heat exchangers underneath the lower belt. I will explain it a little bit later why we are doing it this way. So we have quite a bit of number of heat exchangers, but it provides a really large advantage for the overall process of the drying system. Here just a short indication of the airflow direction through the dryer. So it's really in each module, the air starts from the bottom, makes its way through the belts and through the sludge layer to the top, where we have the process fan, and then the process fan pushes the air to the next adjacent module, where the air starts again the travel through the sludge layers. First it hits the lower belt and then it hits the upper belt, goes back to the next process fan. And by doing that, so we are generating, or we are creating a helical flow, so a spiral flow of the drying air through the dryer from the headpiece 1 all the way then to the headpiece 2, where the air is discharged and then further treated either through a condensing system or directly discharged into an odor control system. So these heat exchangers are all operating with hot water. So that gives us really a high flexibility when it comes down to the hot water supply. I will show a little bit then later how many different options we have available. And then the hot water is distributed to each of these single heat exchangers through through modulating valves. So every single heat exchanger the temperature is controlled by temperature sensors and by the modulating valves. So if the heat temperature reaches the process temperature, we are just keeping the water flow constant. If we need more water because the process temperature in the area is dropping down, so we are increasing the water flow. Like you can see here on the top right corner, so we have the option to really use all kind of different heat sources. Can be a boiler system, can be heat pumps, or any other waste heat which might be available, whether that's coming from a CHP unit or maybe local power plants. So it could be hot water, it could be steam. We would just then apply an additional heat exchanger to transfer the heat to the hot water loop, which feeds the dryer. Here just how these heat exchangers are installed in each module. So this is a picture of one module, and you see, so these blue strings are the belts. You see in the middle more or less the lower belt, a little bit on the upper corner, the blue part of the upper belt, and then we have the two heat exchangers located right below these belts with the heat supply line and the heat, the hot water return line back to the heat source, which could be a hot water boiler, depending on the temperature we are operating the dryer. It could be just a regular hot water boiler, or if you go with a higher temperature of 284 degrees process temperature, we might need to go with a pressurized boiler system. We did some preliminary design work just to give you an idea what the range is of our dryers. So we can process somewhere between 300 and up to 9,000 pounds of water evaporation per unit. So a single unit can process up to 50,000 wet tons a year. Depending on the type of sludge and the dewatering quality, it all depends on the cake solids. What we can normally see, so we can handle dewatered cake ranging from as low as 15%, which is probably mainly waste activated sludge, or up to 35% whenever we have digested sludge or maybe primary sludge. The drying process normally ranges, that's our standard design, between 70 and 92%. And the temperatures we are operating the dryer at is at as low as 185 degrees Fahrenheit. Hot water supply, and like what I talked about earlier, the 285 degrees process temperature inside the dryer is achieved with 293 degrees Fahrenheit hot water supply. We need, in average, about 1,300 BTUs for the drying process, and an electrical power consumption somewhere between 0.02 and 0.03 kilowatt hours per pound of water evaporated. So here just a short summary of the different sizes or the number of dryers we might need for the plant at East End and Westbrook, or for a regional facility as lined out in the RFI. So we have multiple large installations. Here is just an example of for a regional facility. If we would need 3 dryers, we would probably line it up in a way like shown here on the drawing. So just for the dryer footprint and the feeding area, we would need probably a building with a footprint of around 120 feet length and 75 feet width. Just to talk a little bit about the dried material. We are with the type of feeding of the system with the extruder, we are able to generate material which is normally somewhere in the 25 pound per cubic feet range. We can additionally, with additional processes like a crusher or pelletizer, we can achieve more than 40 pounds per cubic foot of the final product. So the overall goal of a drying process is really to reduce the mass and the volume. So we can achieve, just by drying to the 90%, we can achieve 78% reduction in weight and up to 69% reduction in volume. Here, just table of the different sizes of dryers and installations we have. You can see, so it goes from smaller plants with less than 5,000 tons a year up to more than 200,000 tons a year. So these are the different applications with the different temperature ranges, ranging from less than 194 degrees up to the maximum what we have available. I do want to point out that we are able to use different heat or temperature zones in a single dryer if necessary. So if there are different heat sources available, we can apply that to the dryer design and design a dryer system around different heat sources in one unit. Here the largest installation what we are working on right now. It's an installation in the Netherlands with 6 of the largest dryers we have available. So 6 PT30s processing more than 250,000 tons a year. This is probably a similar sized system. It's a plant in Germany. The interesting part here, it's a regional facility located at a cement factory. So they are using the waste heat from the cement factory to dry the sludge and use the dried material right away in the cement industry. That was just a picture of this facility. This is one of the installations we have with 2 different heat levels inside the dryer. So there's one area with 194 and the other half is running at 284. Here just a summary of the modules and a detailed flow diagram of that installation in Innsbruck in Austria. Here in the US, we have currently 9 projects with in total 11 dryer units. So we are the second largest market for belt dryers worldwide. Meanwhile, we have over 50 projects now with 72 dryer units installed across the world. Here in the US, we have 9 installations. It's just a list of the installations. So the first one was started up in 2011, so more than 10 years ago. Overall, dry installations are in operation now worldwide since the early 2000s, so more than 20 years. Here just a summary of the our references here in the US. So one is close by to our office in Mooresville, North Carolina. Just about 45 minutes here from the Denver, North Carolina headquarters of Huber Technology. We have an installation, for example, in Sheboygan, Wisconsin. We have a 2 belt dryer system in Springdale, Arkansas. And if you have any questions, so you can contact me, Dieter Weinert, I'm process manager, also, or Brian Baker, our regional sales director, and Ross Gorbett is always also available for any questions if you have one. Thank you very much.
All right, do we have any questions online or here in the audience? All right. I gotta stop putting that down because it's loud. All right, thank you, Dieter. Appreciate you showing us the Huber belt dryer.
My pleasure. Thank you for the opportunity.
Appreciate it. All right, so our next one before the break, we have, is it Rick who's gonna be coming on for BCR?
That's correct.
All right. Dieter, if you want to stop sharing. Okay, you got that. And Rick, if
I didn't find the button quick enough, sorry.
Oh, we got time. Don't worry. All righty. If there's nothing else, any questions, Uber, let Rick go ahead and go. Actually, wait, hold on.
If you're not presenting, please.
Yes. If you are not presenting, please mute yourself.
Couple Scott Furman's out there who aren't muted. You're making me look bad.
We have the one Scott Furman, Rick, who is presenting, who didn't change his name. we have another that needs to unmute, to mute himself or herself. All right. Go ahead, Rick.
Yeah, thank you, Tracy. Good afternoon, everybody. Thanks for the opportunity to present. I'm with BCR. I'm Rick Tree-Levin. I'm regional manager with BCR. We have this technology as well as other Class A and Class B technologies, but the dryer is the solution for Portland, Maine, as far as a pre-treatment process going into PFAS destruction. And we do have partnerships and relationships with about every quite a few of the technologies out there for PFAS. So I'll go into a little bit about where our partnerships are going and places that we're partnering with. We also have as an option the Savar belt dryer unit out of Germany. And I'll go ahead and because we have a short time period to present both those technologies, I'll probably go ahead and present the Savar option as well. Real high quality belt dryer if that's the way that the decision is made to go that way. All right. All right, can you see my slides changing?
No, it's not changing.
Okay. All right, I have it in the slideshow mode. Let's see. Okay.
Yay, got it.
All right, good, thanks. Yeah, so anyway, a little bit about BCR. We acquired the technology that we use, the ThermoFlight hollow flight technology in 2015. They had, close to 100 applications in the hollow screw in industrial applications, and we were able to take that in a municipal direction and have worked with the existing clients to modify those and improve those. And we have made a lot of changes, a lot of changes that made a big difference. And now we have a real high quality unit that, with a prediction of life based on the finite element analysis that we do and all the quality control checks that we do about 40-year life for the major components. So we really build a high quality unit built to last, 100% fabricated in the US. And that's all we do is biosolids. So we focus on sustainable biosolid solutions for Class A land application in areas where we still can do this in the other parts of the United States. And then pre-treatment for drying for pyrolysis or gasification where that is required. And looks like that's going to be required for sure in the Northeast and maybe in many of the other places in the country. Okay.
Your slide doesn't seem to be advancing again.
Yeah, I'm having a problem with that.
Do you want me to take over sharing?
Yeah, if you could.
All right, let me start that. All right, you have to stop sharing so I can take over. Rick, you got it. Can you stop sharing?
Yeah, I hit pause share. Is that?
No, you have to stop it.
There it is.
There it goes.
It
All
came
right.
up. Okay.
All right, so then here. All right.
All right, so drying is pretty key when we're talking about pre-treatment for pyrolysis or gasification. It's got to be dried. And you can either dry it to 70% for pyrolysis or gasification, or if that's not an option, just to dry it as much as you can to get the volume reduced as much as you can, go into a landfill with PFAS. So either way, we design the PWD plants for getting as dry as 95-98%, just removing all the water so it gets as dry as possible. If that's all you're going to do is put in a truck and take it. Obviously, if you're drying at the plant, shipping dry product is a lot less expensive. You're taking a lot of trucks off the roads than taking a wet product over to a regional facility. So we do have experience with both, where they centrifuge and take it to a regional facility and then dry it, or you can take a dry product to a regional PFAS destruction facility, either way. Or in their case, they could do it all on site. So you're reducing traffic on the roads and the hauling costs and greenhouse gas emissions. And we're making a product that could be stored if it is a product at the end that could be land applied. It could be stored all winter and applied as a fertilizer down the road, but not in Maine, but other places. Next. All right. This is the layout, the process flow diagram for Wisconsin Dells, and it's pretty similar for all the applications that we have. We are an indirect heater, and we have a thermal heater, oil heater, a thermal oil heater that heats the process oil that gets pumped through the dryer and dries the product out. This is a sealed vessel, and 20% of the drying is coming from the outside shell of the dryer, and 80% is going through the hollow screws and back, and that's drying the product with the highest amount of heat transfer rate per square foot. The product gets up to 240, 250 degrees, so we get almost automatic pathogen control, so it's all class A. Our thermocouples are right in the material itself, and it's a small enough material where we don't have any issues getting class A approval from regulators. And then we have to cool it down, though, since it is so hot. It's cooled down in a discharge conveyor through the cooling conveyor, and that gets the temperature down to where it can't self-ignite, and gets the temperature down to where it's ambient temperatures. It's all got rotary airlock valves, so we have very little air that could get in. So we're operating an airflow that's, about 100, 150 CFM, which is way below what belt dryers operate at, 1 to 3,000 CFM. So we don't have air in the system enough to where we have a combustion issue or a fire issue. So we meet all the NFPA standards and don't have issues. We monitor the oxygen. And then as an extra safety precaution, we do supply a nitrogen generator. And that nitrogen generator is a real efficient, 99% efficient to create nitrogen out of air. And for not a lot of cost, we add that nitrogen in the system, which does two things. It makes a very safe drying environment. It also, because you have nitrogen and not oxygen available, you don't have corrosion on any of the carbon steel parts. So where you do have in the cooling conveyor, where you do have a change of temperature, where you could have condensation, we do use stainless steel, but it's not required everywhere else. The condenser condenses the condensable gases. It's a 3-stage condenser. And then the odors or the non-condensable gases, which again, there's just few because of the low amount of air coming through there, goes through an odor control, chemi-absorption odor control unit. So it's a pretty simple system with a small footprint. We do get involved with designing the hoppers. We can supply the hoppers, design those based on the dewatering rate. We supply dry handling facilities, dry handling conveyors and such. If that's would like that to happen, we can design and supply those as well. All right, here's a picture of an application in Wisconsin Dells, Wisconsin. As you can see, first off, it's real clean. This isn't washed down before the picture was taken. This is the way it operates. Again, it's slightly negative with no odor getting out or dust getting out of the system. So it's fully contained and very clean, good working environment for everybody that's working on it. It's a small footprint. You got the hoppers in there. You've got the dry product storage bagging facility here on the left. All this can be set in probably the smallest footprint of any dryer in a small area. The dryer is only, for the project we're talking about, the dryer length would be about maybe 53 feet. That's the largest dryer we make for the Portland facility. And if we go to a regional at Portland, it'd probably be 2 dryers of the same length. So 2 of them side by side at like 50 feet, 53 feet long. Together, you might need 70, 80 feet just to give enough room around it. But it's all class 1 div 2 within 10 feet. And then because we have no dust that escapes, the whole room is not classified. And so we can put the controls and motors outside that 10-foot envelope. Okay, here's just a picture of how the oil, the hot oil circulated through the auger. And again, it's coming in one side and coming back out the other, going through the hollow flights themselves. Again, to have the smallest footprint, the highest heat transfer. So it's a very efficient heating system with getting down to total, in some cases, depending upon the sludge, down to 1050 BTUs per pound of heat required. So it's a very efficient system as well. Here are the self-cleaning augers. Again, they're twin augers. They're both hollow. They, again, it's simple. They move slow, so you have very low wear. The hollow flights come together to clean themselves, and to also move the solids along, chop them up a bit. We rock them back and forth as it moves, and releases the steam, and just conveys that material along to the end, and that's how simple it is. So it's simple, low maintenance, and safe, which is critical for unattended when we're talking about 24 hours operation or 13 hours. You have to have a system that you can look away from and not worry about it. And so we have a lot of years of experience of running 24 hours with people checking in on maybe their iPad at home, turning them on at home, getting it all warmed up so that when you get to the plant, they just start running and making product right away. So it's sealed, it's positive slow auger speed with minimal wear, very little maintenance, either daily or monthly or weekly. They use a grease gun for the fittings. They make sure the alignment is good as you want to make sure the alignment is such that you don't have any wear on any of the parts. And if you do that, you have, again, low maintenance. There's a bearing, a split bearing on one end, on the hot end, that needs to be replaced maybe every 6-8 years and maybe rotated a little bit more often than that. But you can get twice as much life by using a split bearing, and that's one of the areas that requires maintenance, but can be taken apart without taking the whole system down for very long, maybe an hour and a half. And that's about it for maintenance. Again, like another dryer, it's got low electricity. There's no fans and blowers. And so we have we have the feed pump and just very few other parts that keep electricity. Like some other dryers mentioned, they mentioned we can dry anything. It's true of the BioScrew here. We dry digested sludge or undigested or partially digested. It can be septic, silty high. It's just a matter of designing. We do demos in a lot of cases to where we can demo the sludge and know about what the characteristics are for drying before we go ahead and finalizing design. But we can dry from 13% all the way up to 30%, and give you a product from 60 to 90%. So it depends, or 98%. So it depends on the conditions, but you can avoid a lot of cost of digestion and thermal hydrolysis and all that with with just designing your dryer to handle all that sludge. If you do go ahead with anaerobic digestion or aerobic digestion, it will dry better, but it'll just take a little bit more heat maybe, but it can be dried. These pictures are just showing how it goes through phases. It just goes through like a sticky phase to the end of its granular. I wanted to mention that we build all sizes dependent upon the plant sizes. So there are a number of plants, smaller plants, considering putting dryers in. So we can build dryers for like 0.2 MGD. We built we proposed a unit for 0.2 MGD down in Ohio, where they've had a dryer before that needed to be replaced, and it's probably the size of our demo unit. So we can build from that small all the way up to regional facilities that we have in both Wilmington, Delaware, and Long Island, New York, where they're much bigger, and there's a couple of them about the size of what be going in at Portland. So we typical design are from 800 pounds an hour to 12,000 pounds per hour. And those would be the sizes that's required for the Portland project. So we'd be looking at one for the current rate and 2 of them for regional facility. The IC 12,000. So the other nice thing about having a sealed vessel is that all the temperatures and the oxygen sensors are all very accurate. It's sealed, so we don't have any influence from air. And when you have accurate sensors and sensors that are reliable, you can run it automated, and we can run based on knowing what temperatures at our discharge, and having VFDs on pumps. We can fine tune this to almost have it run itself, and it's it's something that can be done. So what we have for a product at the end is a granular product that looks like dirt. And for PFAS destruction, that's what the gasification companies really like about our product, is it's granular. So it's really the size that flows well, and that they get the most consistent PFAS destruction is having a product like what we put out. So that's why we're working with a couple gasification companies that have chosen our technology. If it does go out to be land applied, we can either just dry it maybe to a little bit less, around 90%, to cut down on dust, or a pelletizer can be added to make it a pellet and make it more uniform. So these are a few of the regional drying processing installations that we have in Wisconsin. Dells is a seasonal facility where we designed the model to handle low flows in the winter and high flows in the summertime. Tri-Lakes is one in Branson, Missouri, where they have 4 other facilities that now it's up to 4 now, that bring their centrifuge solids into the facility in Branson, and then they dry it with one dryer for all the different facilities, and they collect tipping fees to be able to help pay for the unit. The Wilmington, Delaware project, they hired Honeywell Corporation to reduce the carbon footprint and provide a system that uses renewable energy. And they have a very efficient system running there in Wilmington, Delaware. And then Clearflow Technologies is a recycle waste facility that has two big units in Lindenhurst, New York. And they also run on waste heat. They have a waste kiln that supplies the waste heat to run the dryer. Here's a picture of the Wilmington, Delaware. This would be about the size. They use silos to go into it. Like I said, they use both waste gas heat, which becomes a very efficient drying process with hardly any, with significantly reduced electrical energy and hardly any natural gas usage. We work with Jacobs as a DBO and operating company in Wilmington, Delaware. So we've got good relationships working with in a DBO type of arrangement with management, and then we have service programs to service the unit if that's required. And just if you do a few service items and watch that maybe once, twice a year, you really have very little maintenance on equipment. So just a kind of summary, the system's versatile. We can work with any operating schedule, and we have a compact footprint, again, reducing space. A lot of times we don't need an extra building for smaller systems. We can work in the dewatering building or the truck bay. Safe and simple and automated. We have a dense product without pelletizing. We're at 40 pounds per cubic foot, which is quite a bit denser, and we can use smaller trucks. It's a consistent granular product, which again, which they like for going into PFAS destruction. And then I just want to mention that we have demonstration units. We demoed at 2 places in New Hampshire. I think they like what they saw. We can figure out what the efficiency is for BTUs per pound of water evaporated. And we do have another trial going on in September. I think it's pretty well set in stone. We'll be up back in New England this early in September to run demos there if anybody's interested in seeing the unit. We do run on electricity on the demo unit. We can run on electricity for smaller units, becomes cost effective. And then, like I said, we have proven the technology with gasification. We use that gasification energy to heat our dryer. We do have the flexibility of turn down and running at a real dry product if we're just going directly to landfill. This would be a picture of the site that's being proposed for the Portland project. It's got a compact footprint itself for the gasification system itself. So with that, I'll turn it over to the Save Our portion. We have just a few minutes. I just want to cover this quickly. That Keith Hamilton is the salesman for the Save Our unit in the United States. He's available. Next. Like other belt dryers, they can use waste heat and either heat indirectly or directly with natural gas. They've got very good control philosophy and odor control. Go ahead next. They again work with other project managers and DBOs providing technologies. They've got good references worldwide with 5 references in North America, with a new one going into Honolulu if anybody's over in Hawaii. And they've not, obviously you don't get PFAS destruction from drying, but it is where if it's a large application that they can dry consistently like they do in Howard County, and then you can take it to PFAS destruction. So they've got a lot of experience with good engineering teams that we work closely with. BCR provides a lot of the services if they decide it's better for us to do it rather than having German people coming in. And a lot of that, just quickly on the technology benefits, is they've got a proven injection system, distribution system that's patented and works out well, where you don't have any problems making the noodle strands going across the belts. It's a stainless steel belt, which is unique, that comes in plates. If one portion of it needs to be replaced, you don't have to replace the whole belt, you just replace that plate section. It runs again on low temperatures and uses of various drying sources of heat. So I think we're towards the end of our presentation time. But again, it's what's really neat. You visit the Howard County facility in Maryland, and you see that how efficient it is. It uses digester gas 100% and has a very, very efficient system. And that just kind of shows the distribution dosing system with the rollers that give you a system without extruding pumps. It does it with a roller system, roller press, that feeds down to a 2-pass belt system on stainless steel belts. So with that, I guess we'll be finished. I ran out of time, but we did present earlier to Brown and Caldwell. We'd be happy to re-present again if there's any questions. I can take those questions.
Great. Thank you so much. Is there anyone online or in person who has a question? I did have a question on your smaller electrical systems, electrical dryers.
Sure.
What size, are they just for the smaller size where it makes sense? Or is it a certain dollar cost per kilowatt hour?
Yeah, they make sense where you have low cost of kilowatt hours. So we've done return on investments. We can do that study for you if you have a system. There's an application in New Hampshire where they're looking at using solar power and that can run their smaller unit. We did provide big units for like Niagara Falls. We proposed where they have very low cost of hydroelectric power. And in that case, it looked like the electric heater was cost effective, but it is a lot more costlier thermal heating unit. And so we'd have to look at the increased capital cost versus what the power cost would be.
All right, great, thank you. All right, if there are no other questions, here is Rick's information. And also talk to Rob, if you don't get Rick's. And we are going to break. And what time does it end at? I don't have my schedule in front of me. So 2:55. So 2:55, we'll start back with the next round of presentations. Thank you, everybody.
Yeah, thank you.
Yeah, and thank you, Rick, for presenting. Appreciate it.
Yeah, thank you, Tracy.